Hi, everyone. My name is Neil McIsaac. I'm a Microsoft technical trainer within Worldwide Learning here at Microsoft, and I'm responsible for providing technical skilling on Microsoft's cloud technologies to our top enterprise customers. I've been in the IT industry for over 30 years now, and I've been working in the AI and business intelligence space since around the early 90s. I've also been supporting Azure since 2008, which is about 2 years before Azure was generally available to the public. And with that, I'd like to welcome everyone to this course on designing and implementing a data science solution on Azure. The target audience for this course are data scientists that want to learn how to build, test, and operate their own AI models using the Azure Machine Learning Service. So our focus will really be about using the service. The expectation is that everyone taking this course is already familiar with the fundamentals of developing machine learning models. For example, you should have some experience working with frameworks like scikit-learn, PyTorch, TensorFlow, those type of things, and are familiar with working in Python to develop and manage machine learning models. That being said, we get a lot of people that are not data scientists attending this course, and that's absolutely okay. I would, however, highly recommend that you check out our AI 900 Fundamentals course, as well as get some practice using Python to get the most out of this course. Coming back to what we'll be covering in this course, more specifically, we'll start things off with how to design a machine learning solution. We'll then explore the Azure Machine Learning Workspace. We'll spend time examining the tools that we'll use to work with the workspace, and we'll also discuss how to configure the workspace for our needs. We'll then talk about how to create experiments using the automated machine learning service and how to track model training with MLflow. After that, we'll spend some time on how to optimize our model training using jobs, hyperparameter tuning, and running pipelines. We'll then review how to manage and review models within the service, including how to use the responsible AI dashboard. Lastly, we'll finish the course up with how to deploy and consume the models in a production environment. Before we begin, it's worth noting that this course aligns with the DP-100 certification exam. I, for one, am a big advocate for certification, and I'd encourage everyone to consider becoming certified at the end of this course, and here's why. Let me ask you a simple question. How do you know you've learned everything that you should about the Azure Machine Learning Service? It's not as simple of a question as it seems, is it? So here's the thing. When we here at Microsoft develop a course and a related certification, we actually reach out to the industry and partners and ask, what should somebody working in this space know and what level should they know it at? So you can think of the certification as really being a set of learning goals that your peers in the industry have helped to establish. So try not to think of it as just a piece of paper that isn't really relevant to you, but rather try and think of the certification as your overall learning goal. In other words, if you have learned everything that you should about using the Azure Machine Learning Service, then the certification exam should be easy. If it isn't easy, then you probably have a bit more learning to do. And also, as a side note, I always like to remind our customers that I'd rather have them make a mistake on one of our exams than make a mistake on a real-life project that they're implementing. Ouch. All right, hopefully I've managed to change some minds out there about becoming certified. With that, let's get started with designing machine learning solutions. There are many options to train and consume machine learning models within Azure. Before we start a project, we really should plan some of the time around designing what our overall solution should look like. We need to consider how data will flow from their original sources and the physics of how we'll prepare the data that we'll use for the model training and testing later on. We also need to think about the overall process that we'll use to build our model and make decisions such as what type of model to train or perhaps what services we need to use. We'll also need to think about how our model will be consumed when it's deployed into a production environment. And lastly, we should start thinking about how to best scale and maintain our solution over time, what we often refer to as ML ops, which is short for machine learning operations. Let's get started with designing a data ingestion strategy. Data is the most important input for your machine learning models. You'll need to access data when training machine learning models, and the train model needs data as input to generate the predictions. The catch is that it's extremely rare that we can get the data from the original source system because we usually need to do a number of things to the data to prepare it before we can actually use it for model training. As well, we usually don't want to impose any extra workload on the production systems hosting the original data. So we need to figure out where the original data is hosted and determine a strategy to extract that data efficiently and prepare the data for model training. This is referred to as an ETL or an ELT process. ETL stands for extract, transform, and load, and ELT stands for extract, load, and transform, just reversing the load and transform. This can be done using many different technologies, which we'll talk about shortly. In the example on the slide, you can see the original data is in a JSON format, which is then converted to a table format while doing some preliminary transformations with separating the date-time value. And then the last transformation, we've dropped the device ID column and removed the seconds from the time. Couple of things here. First, it's worth mentioning that one of the biggest advantages of using the cloud is being able to separate compute away from storage, which helps with the overall costing. The benefit here is that we can focus on prepping our data in the storage layer with little to no compute costs. And then when we need to process our data, such as for model training, we can spin up the compute to do the work, and we can have it go away when it's done, reducing the overall costs. We'll be covering compute options later on in the course. As for the data options, you have a lot of options. The three most common options are to use Azure Blob Storage, Azure Data Lake Storage, Gen 2, right, our newest one, or perhaps an Azure SQL database. Azure Blob Storage is the cheapest option for storing data as unstructured data, which is great for storing files like images, text, and JSON, things like that. For data analytics and machine learning workloads, CSV files are one of the most common data formats used, but there are plenty of other formats for storing data within the file system as well, like perhaps Parquet files. Azure Data Lake Storage, or ADLS for short, is a more advanced version of Azure Blob Storage. It can also store text files like CSVs, as well as images, but it has some additional features that are useful for data analytics style workloads. ADLS supports a hierarchical namespace, aka folders, and it also supports a more granular permission model, which means it's easier to give someone, or perhaps a service, access to a specific file or folder. Since ADLS is built on top of the Azure Blob Storage service, storage capacity is virtually unlimited, so it's really ideal for storing large amounts of file-based data. Lastly, you can't really go wrong with using an Azure SQL database. This is one of the cloud-based versions of our popular SQL database platform. This can be useful when you want to store data as structured data within a relational database. Definitely a great choice when the data is very structured already and doesn't change much over time. The next thing that you'll need to consider is how the whole process is going to physically go. We typically refer to this process as a data ingestion pipeline, which is simply the sequence of tasks that we need to do to get our data from its source to its destination, which in a machine learning workload is to have the data prepped and ready for model training. It's important to note here that the process is usually being performed outside of the machine learning service. Although we could use the Azure Machine Learning Service to perform those ETL or ELT operations, there are some better tools that are much more dedicated for the job that are readily available to us. The two most common tools that tend to get used are the Azure Synapse Analytics Service and the Azure Databricks Service. The overall process here that's illustrated on the slide is to extract the data from the source, use a service such as Azure Synapse Analytics to perform the ETL, ELT operations on the data, and then output the prepared data to one of the storage services like ADLS, where it can then be consumed by the Azure Machine Learning Service. Since this course focuses on the Azure Machine Learning Service, we won't be getting into the Azure Databricks or Azure Synapse Analytics services here. If you'd like more information on either of those products, you can check out our DP-100 course on data engineering on Microsoft Azure using the link below. Lastly, establishing the ingestion pipeline definitely takes some work to set up, but it's also important to think about the process over time. So what do I mean by that? So think about this. If you processed your data and trained your model today, your model will only know that data that we used today. It won't know any of the data that you might be collecting moving forward, like tomorrow. So we might need to consider a couple of things. How can you streamline the process to add new data without reprocessing all of the data? When do we need to retrain the model? Are we evaluating the accuracy of the model with the new data? Has our new training data drifted? In other words, just because we have new data, it doesn't mean that we need to retrain the model. Data drift is when the new data is statistically different than the older data. So how do we determine that? For now, the point is this. We need to think about this data ingestion process over time. As a data scientist, your focus will be on training machine learning models. Once you have the data you need and it's been properly prepared, you'll need to have sufficient compute to do the model training. To be efficient and cost-effective, you need to choose the appropriate service to train the machine learning model. You need to know what type of model you're training for your situation. You'll also need to understand the requirements of your model so that you can design a model training solution that ensures that the model keeps performing as expected and stays relevant over time. As a general overview of this process, we start with defining the problem. We need to decide on what the model should predict and what the criteria is for it to be considered successful. We need to get the data. Where is the data stored and how do we get access to it? We need to prepare the data for model training. We discussed this previously. We need to clean and transform the data and have it ready for model training. Then we'll train the model. We need to choose an algorithm and hyperparameter values that give us the most accurate model. We then need to integrate that model into production, which means that we need to deploy the model to an endpoint that could be consumed to generate predictions. And lastly, we can't forget that we need to monitor the model so that we know how it's performing over time. Machine learning models are based on algorithms, and those algorithms are broken down into many categories. By the way, I'm sure all the data scientists taking this course are already familiar with this, but it's worth reviewing, especially for those that might be watching this that are newer to the data science field. So, 5 common categories that you really should be familiar with are classification, which is used to predict a categorical value, like what group something belongs to. Regression, which is used to predict a numerical value. For example, to understand the relationship maybe between marketing costs and sales revenue. Time series forecasting, which is used to predict future numerical values based on time series data. And the easiest example of this one would be to predict, stock market values. Computer vision models are used to classify images and detect objects in images. An easy example of this type of model would be in quality control systems, maybe for manufacturing plants. Lastly, natural language processing, or NLP. These models are used when we need to extract insights from text. That's a very high-level look at some of the categories of machine learning algorithms that are used to build models. There are a lot more to know about the details of individual algorithms, such as what hyperparameters you should set and what values you should use for them. However, just as a reminder, in this course, we won't be going into any of the details on the data science side of things, like the details of how to best use those different algorithms. Our focus is going to be on using the Azure Machine Learning Service. So, speaking of the Azure Machine Learning Service, we happen to have other services that are also capable of creating models, not just the machine learning service. So going from left to right here, we have Azure AI services, which is a collection of pre-built, the keyword here is pre-built machine learning models that you can use for common machine learning tasks, such as object detection in images or speech to text. These models are accessed through an application programming interface, API, so you can easily integrate a model with your application. Some models can be customized, or I think a better description is they can be enhanced with your own training data. The upside of this service is that it provides ready-to-go models that can be leveraged in a production environment very rapidly. The downside, though, is that the models are pre-built, right? So aside from being able to enhance some of the models, you can't fully train your own model based on your data with that service. Next is the Azure Synapse Analytics service. Azure Synapse Analytics is primarily designed to ingest and transform data at scale, but also includes several machine learning capabilities. To train models with Azure Synapse Analytics, you can use Spark pools using MLlib. You can also use the integration between the Azure Synapse Analytics service and the Azure Machine Learning service to train models. But that's really an integration component between Azure Synapse Analytics and Azure Machine Learning. Next up is Azure Databricks. Azure Databricks is a data analytics platform that you can use for data engineering and a lot of other data style workloads, and also use it for data science. Azure Databricks uses distributed Spark compute to process your data, and you can choose to train and manage models using Spark and MLlib or other libraries similar to what we would do in Azure Synapse Analytics. You can also integrate Azure Databricks with other services such as the Azure Machine Learning service to work with your models. Lastly is Azure Machine Learning. Azure Machine Learning is a service that is focused on machine learning and gives you many different options to train and manage your machine learning models. You can choose to work with the Studio for a UI-based experience or manage your machine learning workloads with things like the Python SDK or the Azure CLI for more of a code-first experience. It can be fairly daunting to compare these services. The short version is that the Azure Machine Learning service is the preferred service generally to do machine learning workloads. Azure Synapse Analytics and Azure Databricks are commonly used for other style of workloads, such as data engineering tasks, but have machine learning capabilities. And Azure AI services is best used when you want to use pre-built models. When it's time to train your model, the most valuable resource you'll consume is compute. It's important to choose the most suitable options for compute, and you should monitor your compute utilization to know when to scale up or down to save on time and costs. Trying to figure out which option best fits your situation is an ongoing process. You'll need to consider some of the following compute options. So, CPU or GPU. CPUs will do the job, and they're cheaper to use, whereas GPUs, right, the graphical processors, will be more powerful and can be effective whenever we're working with unstructured data like images, text, or maybe large amounts of tabular data. The downside to GPUs is that they're more expensive, but since they can usually process the data faster, they usually don't have to run for as long as a CPU. The actual cost will require some experimentation for you. It really depends. General purpose or memory optimized. General purpose virtual machines have a balanced CPU to memory ratio, which is ideal for testing, development, especially with smaller data sets. Memory optimized virtual machines have a high memory to CPU ratio. So these are usually great for in-memory analytics, which is ideal when you have larger data sets or when you're working in notebooks, for example. Services like Azure Synapse Analytics and Azure Databricks offer Spark compute. Apache Spark is an open source distributed processing system used for big data workloads. It utilizes things like in-memory caching and optimized query execution for fast analytics queries that will run against any size of data. When we're thinking of configuring compute, Spark lets us distribute the workload across multiple virtual machines very effectively. Every time you train a model, you should monitor how long it takes to train the model and how much compute is used to execute your code. I would suggest that you occasionally test these different options over time to check to see if you still have the most optimal configuration. Remember that our overall goal is that we need to get our model into production in order for it to be useful. We can't just make them and leave them on the shelf. How we intend to deploy the model can impact how we train it. Once the model is trained, we need to deploy the model to what's called an endpoint. The idea here is that once the model is deployed to an endpoint, an application can send requests over to the model and get a response back with the prediction. Endpoints are simply the location where we'll send the API calls. The biggest decision that you need to make here is whether the model will be deployed to a real-time or to a batch endpoint. Real-time endpoints are used when an application needs to call the model and get an immediate response back with a prediction. Batch endpoints are used when we collect a whole bunch of data over time, and then we want to process all that data in batches. So, such as processing the data nightly to generate prediction data. Real-time deployments need to be hosted with continually executing compute. So even when it's not being used to generate predictions, you're still paying for the running compute. Batch endpoints, on the other hand, will spin up compute on demand and then stop after the batch processing is finished. Batch also has an advantage of being able to process the data in parallel, so it can process large amounts of data more efficiently. If your predictions can wait more than 5 to 10 minutes, it might be better to use a batch endpoint since that's enough time to spin up the compute on demand. All right. Let's discuss how to design a machine learning operations or ML ops solution. First, what do we mean by saying ML ops? This is actually a pretty complicated subject. If we take a step back from training a model, we need to ask ourselves things like, how do we move our solution from a proof of concept or development environment into the production environment? Considering that our development environment is typically smaller, how do you ensure that our solution properly scales in a production environment when it has a lot more training data and just simply being consumed a lot more? Can we redeploy our solution to another environment easily if we need to? The overall goal here is to make our solution robust and scalable and answer those questions as best as we can. First, we need to think about separating everything into different environments. A typical approach would be to have 3 environments: development, pre-production or QA, and a production environment. This is best done by having 3 different machine learning workspaces. That way you can separate access to each environment more easily by controlling access to each one with role-based access controls, or RBAC for short. It's also fairly common to separate the workspaces by hosting them within separate Azure subscriptions, which can give you another layer of management and control of the environments. When we separate the environments, we need to think about the role that each environment plays. For example, usually we see the dev environment used for conducting experiments for that initial model training and testing. Then we can move the best models over to the pre-prod or QA environment for more rigorous, thorough testing. And then we'll move the approved model over into the production environment where it will be deployed to an endpoint. The point here is that we don't need all of the same services or permissions in all the environments. The production environment, just as an example, is really only used to host the deployed models. So we probably don't need to handle model training and testing or need to grant access to the data scientist. The thing is that your solution and setup will be unique to you, and you'll need to work out the finer details of your solution. You'll also need to consider how to separate responsibilities across your team, as well as consider the iterative approach that happens as we continually improve our models. It's also worthwhile to note here that if you're a data scientist, a lot of this setup will be outside the scope of your role. On this slide, we have an example approach for ML ops. This isn't to say this is the way to do it, it's just an example, but it can help you get started. First, we need to create all the necessary resources for the solution. If you're sticking to the previous example, that means that we'll need to create 3 machine learning workspaces, but we'll probably also need 1 or more storage accounts. We might need multiple subscriptions, and we'll need to make sure only the right people get access to those necessary resources. For example, for the storage, we'll need the data engineers to have access as well as the data scientists. But neither of those roles probably have access to the production environment directly. Next, we'll want to establish the process on how we train and evaluate the model. This will be the main job of the data scientist and most likely being done within the dev environment. We then need to consider how we'll package and register the model, followed by deploying it to the outer loop, which is really about deploying the model to the pre-production or QA environment, so we can do more thorough testing there. In step 5 here, we're finally promoting the package to the production environment where we'll host it in an endpoint and monitor its performance in step 6. Monitoring is also a big part of an ML ops solution. You'll want to monitor the model, the data, and the infrastructure to collect metrics that help you decide on any necessary next steps to improve your solution over time. To monitor the model in production, we usually just examine a small set of data and evaluate if the model is still performing as it should. We should also be evaluating the model for responsible AI issues, such as fairness as well. With respect to the data, our biggest concern is that new data may be introduced with what's called data drift. As I mentioned earlier, it's not new data that drives the need to update a model. It's when the data is statistically different than the old data. As soon as that happens, which is referred to as data drift, then we need to reevaluate our model. Although this isn't usually within the role of the data scientist, we also need to monitor the infrastructure to make sure that we're keeping our costs to a minimum, as well as optimizing performance. Here we can use Azure Monitor to help identify costs, and we can set things like alerts so that we can be notified if any issues might occur. Azure Monitor can help keep tabs on all of the services to help ensure that it's running as it should. To recap, we spent a lot of time on design considerations for an Azure Machine Learning solution. We started with how to design a data ingestion solution by identifying your existing data sources and how you want to serve the data to the machine learning workspace. Followed by how to design a machine learning solution by understanding the different development environment and compute options. Then we discussed how to design a model deployment solution based on the requirements of how your model is being consumed. And then we wrapped up with how to design a typical ML ops architecture and understand the process from a data scientist's perspective. I hope that this session has been useful to you, and I'm hoping that everyone will continue along their learning journey with the next video in our series, where we'll focus on working with the Azure Machine Learning Workspace. See you soon. Hi there. My name is Neil McIsaac, and I'm a Microsoft Technical Trainer. As a data scientist using Azure, we'll tend to use the Azure Machine Learning Service to train and manage our machine learning models. In this video, we'll learn what Azure Machine Learning is and get familiar with all of its resources and assets. In this video, we'll explore the Azure Machine Learning Workspace. After that, we'll look at some developer tools for workspace interaction. And then we'll look at how to make the data available into an Azure Machine Learning Workspace. Then we're going to look at compute resources in Azure Machine Learning. And the last thing we'll be discussing will be what environments are and how to use them within the Azure Machine Learning Workspace as well. So let's get started with looking at the workspace and the resources and assets that we have available to us to do those machine learning workloads. So as we previously introduced in the first video in the series, the Azure Machine Learning Service is designed to focus on training and deploying machine learning models. And the primary audience for this service are really data scientists. When we create a new Azure Machine Learning Service in Azure, it comes with a set of resources and assets that we would use to work with our data and models. It's also important to remember that the Azure Machine Learning Service is still within Azure and is governed by the architecture of how services are managed within Azure. So a couple of things here. First, our Azure Machine Learning Service is depicted on the slide here as a beaker kind of shape, marked with the number 4. Above it, we have a resource group, since every resource in Azure needs to belong to a resource group. Above that, we have the subscription. The easiest way to describe the subscription for those that are new to that is that subscriptions are the way that we essentially pay for services. So an organization can have multiple subscriptions for different purposes, such as a subscription for production and a subscription for development and testing. And this can also provide a management separation as well. Above our subscription is really just Azure itself, which is represented here as the cloud symbol. So that's what's above our service and describes the space that our service works in. When we provision the service, we get 4 related services, really 3 plus an optional one, that are provisioned when we provision our Azure Machine Learning Service. Those services are an Azure storage account that's used to store all of the metadata and artifacts directly related to our service and can be used to also store data that we could use for model training. However, it's pretty common to connect to other data sources such as other storage accounts or data sources such as databases from our machine learning service, which we'll look at later on in the course. We also need an Azure Key Vault. The Azure Key Vault service is used to store secrets, and it's a really common service that we use across Azure to store secrets for lots of other services and applications. With respect to the Azure Machine Learning Service, the Azure Key Vault is used to store things like usernames and passwords and connection strings for data sources that we need to connect to. The next service that's required is Application Insights. This service is used to record all of the telemetry so that we can monitor our deployments using a service that's designed for that specifically. The last service here is the Azure Container Registry, and this one is optional when we deploy the service. That being said, we almost always want it. This service is used to store container images that we use for providing environments, right, to the Azure Machine Learning Service. When we provision the Azure Machine Learning Service, we can see and manage the service within the Azure portal, which is what the image on the slide is showing. There are some things which can be easier to manage with this interface, such as managing permissions to the service by configuring the access control settings. However, most of our time will be spent in the Azure Machine Learning Studio, which can be launched using the Launch Studio button or by using the Studio web URL in the top right corner of this interface, which connects to ml.azure.com. In this course, we'll be spending most of our time in the Studio interface. Let's go over to the Azure portal and see how to provision the service and get a brief introduction to the Azure Machine Learning Service and the Studio interface. All right, so the first thing that we want to do is go and create the resource, right? So let's go up to create a resource in the Azure portal, and we're going to go search for the Azure Machine Learning Service. So let's do a quick search here. Close some windows. We can see that it's right here, so let's create that and get this going. And so we're going to put this into a resource group. I'm going to make a brand new one. So let's call this, how about RG DP-100 Labs. This is really just to organize our resource groups. Let's give this service a name, which for this one, how about Neil's demo maybe, or let's change it to DP-100 demo. There we go, even better. So we can choose what region, so where in the world this is going to exist. I'm a little partial to this one, so Canada Central. And here are the different services that we need to create with this. So these are the 4 services that I mentioned. We have the storage account, the Key Vault, the application insights, and container registry. And the storage account, of course, is really important. So all of these are listed in here. And the first 3 we really need to have, but you'll notice that the container registry is marked as none. So if you don't have one, these all default to being new, right? So you can see that if you did have an existing storage account, you can drop that down and select it. And the container registry, of course, is optional for that. The next thing we have is networking. So we do have options to make the service very private if you want to. That's common, but we're going to leave that as public. And then encryption. Encryption is really big for us. Notice that there's no option to say no to encryption. It's either Microsoft managed keys, and it's all about storing those metrics and the metadata. It is actually in the Cosmos DB instance. So this is like the core things for the service. And of course, everything is encrypted to us, whether it's in storage or anything. So you can choose between Microsoft managed keys or customer managed keys. And the customer managed keys are where you provide your own keys, and that helps with the security quite a bit. The next thing we're going to jump to is the identity. So if we used our own services instead of creating new ones, we would actually have to set up the security. So any of those existing storage accounts and all that, we would have to set that up so that this service would have access to those other services if they were already provisioned for it. So let's jump into the last little bit. So all of the services in Azure really support tags, so we can apply metadata to everything, so we can identify and help manage it later. So you can fill these out if necessary. And then, of course, the last stage to really create everything is to review it, make sure that the validation has passed, and then we'll go and create the service. So this is going to take a little bit to create, because one of the things about this creation process is it does have to go through and create the other services. Remember that we set the storage account and the Key Vault, et cetera. We set those all to be brand new. So when this is being deployed, those services are being created first. The storage account is being created, the Key Vault is being created, et cetera. And then lastly, the machine learning service will get created after that. So let's get this creating, and we'll just wait for this to go. Shouldn't take too long, but it will take maybe about 2 minutes or so. Since this video has been pre-recorded, we've sped up this section to save you a bit of time waiting for this to complete. All right, so we can see that the other services are all created. The App Insight service, the storage, the Key Vault service. We're just waiting for the machine learning service itself to be created lastly, and we should be good to jump into the service to check it out. All right, there the deployment is complete. So let's go check it out. Let's go to that resource. And as soon as we open this resource, the page that we're on, this is the Azure portal interface to this resource. So, we do see it at the name. It is the Azure Machine Learning Workspace, and we have the kind of the standard portal interface, so things like the overview, all of the different settings. This is a new interface where it's all collapsed now, so you will have to expand these for settings, monitoring settings, and all that. The thing is that this is something that you'd see for pretty much all services. The menu changes a little bit, but it's pretty common. Now, another thing is that we will be using the Studio service quite a bit, the Studio interface rather. And just to point out, though, that something that you can do here is manage the access control. So just to highlight where this is, we talked about these role assignments earlier. So we can add the role assignments to grant somebody access to this service. And this is going to happen in the portal interface. We'll come back to the Studio interface in just a second. So the way you would do this is simply add the role assignment. You can grant the data, the Azure ML data science role or the compute operator role, to be a little more granular permissions. You can go to the custom role. On the overview page, coming back to it, so like I was saying, the Studio interface is the one that we tend to use the most with the Azure Machine Learning Studio, and that'll take us to another interface. I do want to point out that this is just a URL really, and the URL is right up here, right? So the Studio web URL, it is ml.azure.com. This URL gives us also the identity of this workspace, but it's actually possible that you can just go to the ml.azure.com website and then select the workspace when you log in there. So, either of those are fine. So both of these, either the URL here or that Studio button down at the bottom, is going to take us to the Studio. So let's use that Launch Studio. And off we go to a brand new page where we are now in the Machine Learning Studio, right? You'll notice that the interface is quite a bit different. This is very much a purpose-built interface for what we're doing. There's a lot of stuff for generative AI in here. In this course, we're not going to be talking much about it. That's a whole world in itself. We're going to be focusing on building our own models, and so the home page, to get us started. There's a lot of different bits in here. There's coming down a little bit, notebooks, where we're going to do a lot of our authoring for this. So we tend to, as a data scientist, we're going to spend a lot of time on this. So let's just close that, what's new. And we can look at our file system here and go, there's nothing really here. But as we go through the course, we'll see a lot more. So we're also going to talk later on about automated ML, right? So we're going to show you this with a script, but this is where we can do automated training jobs, and we'll talk about what that is and all that. But that's also very much supported here, which is going to be great. Now, later in the course, we will talk about like components and pipelines and everything. And there is another interface here for the designer. And so let's just close that. This is where we can actually use components in a graphical interface to kind of drag and drop and connect things together. I'm going to show you pipelines and components with more with scripts in it. It's actually, I think, kind of easy to play around with that. All right, next up. Data, right? It's a big part of this. So let's take a quick look at data. We see that we can control our data assets and data stores in here. Then there's some more ability than what we're going to talk about. But data assets and data stores are really the foundation of what we're going to be working with kind of day to day. And so so data is going to be a big part of that. All right, let's jump down to compute, the other side of it. So we have data, we need compute. And here you can see that we have 4 bits of compute that are listed here. So compute instances and compute clusters and the Kubernetes clusters and the attached compute. So we can configure all this. Compute instances, of course, are going to be the one that we use for data scientists to kind of work with our data. All right, next up, jobs. So when we have a script that we want to run routinely, like on a schedule, we're going to do this under a job. And We could do this with scripts, so we could schedule them, all that good stuff in there to get the work done. So, things like training and all that have a lot of steps. And it makes a lot more sense to simply queue up a job to do that. And that way we can walk away and do other things while that's going. And of course, the diamond that we're really trying to get to is to have a really good model. So this actually supports, registering models under this list. And we can have those models there that are deployed. So think these are the ones that kind of bubble up to be the best ones that we want to use. And we can see it on this list here, even though we can have a lot more models in storage and all that stuff. And of course, once we have that model that's all approved, we need to host it, to deploy it. And we're going to use endpoints for that. And again, we're going to talk about these, all this stuff later on. But here you can see that we can do real-time endpoints. We can do batch endpoints. Right. We also have, when we're talking about compute, we'll talk about compute more later on, but serverless endpoints. There's a lot more serverless options in here. And even though serverless says, serverless, like there's no server behind it, I think a better phrase is serverless really means like compute on demand. It's just a lot longer to write that, and it doesn't roll off the tongue as well. But it's a great new option to have for all this. So it's so we can get our stuff hosted. Now, lastly, you see the Azure OpenAI mark there. And back here on the home page, we also have all the generative AI models. These models are pre-built. And we can do things like prompt flows and everything with them. Again, in this course, we're not really going to focus on any of that. So, all right, with that, that's a quick overview. Let's get back over to some content and talk more about all this stuff. So let's see what's going on. So when I was showing how to provision the service, I showed it using the Azure portal interface. However, you can also create the workspace a number of different ways, such as using the Azure CLI, which is the Azure command line interface, or we could use ARM templates, or we could do it using the Azure Machine Learning Python SDK, which you can see an example of on the slide here. We'll explore the developer tools a bit later in this video. Earlier, I mentioned that you can set access to the workspace by configuring the access control in the Azure portal. We have 3 common roles that we can set on any resource in Azure. The owner role, which gets full permissions to the resource. We have the contributor role, which has all the permissions of full except the ability to manage permissions. So this is actually a very privileged role. And we also have the reader role, which, as the name implies, allows people to view the resource, but they can't make any changes. We also have 2 unique roles that are specific to the Azure Machine Learning Service. These are the Azure ML Data Scientist and the Azure ML Compute Operator. The Azure ML Data Scientist role can do everything in the workspace except for managing compute resources or editing the workspace settings. And the Azure ML Compute Operator role allows somebody to manage any of the compute resources in the workspace. The reason why these 2 roles exist is because our largest cost in cloud computing, as well as within our Azure Machine Learning workspace, tends to be compute. It's not uncommon for an organization to have data scientists that are really knowledgeable on data scientists, but not as knowledgeable about managing compute resources in the cloud. When that happens, compute resources are often misconfigured and can result in driving up costs. For example, maybe they're left on running when they shouldn't. So to help avoid this, we can assign people that are well-versed in managing compute resources to the Azure ML Compute Operators role, and they can manage all of the compute for the data scientists. The last thing here is that if you want to be very granular with permissions, all you need to do is create a custom rule where you can define specific actions that that role can perform in your Azure Machine Learning workspace. It's important to be able to work with the Azure Machine Learning Service in many different ways. So although we can use the portal interface, which we just looked at, we can also use the Python SDK or the Azure CLI to manage our service with code. So let's take a look at that. Here's a quick example of using the Python SDK. To get started with it, we'll need to do a pip install of the Azure AI ML library. After that, we can connect to the workspace using the sample code here that uses the ML client class to connect to the workspace using our credentials, subscription ID, the resource group that our service is provisioned in, and the workspace name. It's possible to connect to our workspace from anywhere that runs Python. So for example, this code could be executing from a desktop computer outside of Azure. In this course, you'll see many examples of using the Python SDK to manage our machine learning service. Another way to manage our services by using the Azure Command Line Interface, or CLI for short. The CLI is primarily used by Azure administrators and engineers to help automate the creation and management of services, usually within things like CI/CD pipelines. This helps to make sure that the service is deployed and configured efficiently and can be repeated if it needs to be redeployed or recreated in another environment. When we install the Azure CLI on our computer, it doesn't come with machine learning support out of the box. So what we need to do is to add the machine learning extension by running the AZ extension add command and adding the machine learning support. Once we do that, we can then use the AZ space ML command to manage our machine learning service, such as creating compute in our service, which is what the example in the slide here shows. Now, let's see a quick demo on how to use the Python SDK and the Azure CLI to manage our service. All right, so let's first think about creating a resource. In the last demo, we went and used this create a resource button and used the graphical interface to do everything. This time what we're going to do is go over to the Cloud Shell because we want to do this in command line, right, doing code. So we're going to open up this bash prompt. What I'm about to show you, I can show in bash or PowerShell, so it really does matter. But once we're here, the first thing that we need to do is if we want to do the Azure CLIs, we need to add the extension. Now, I'm going to show you how to do this, even though the Cloud Shell already has this extension added for us. But the command that we would do is AZ extension add -n ML, right, for the machine learning name that we want. And it just kind of comes back and says, hey, it's already installed, and we can see the version. So even though we can do this here, it doesn't really matter because it's already installed. However, if you were to do this on your own computer at home, you would need to install this extension. It doesn't come with the Azure CLI included. It's not included with the Azure CLI already out of the box. So it's just a matter of running that command, though. Okay, so after this, let's actually see how to do everything with the CLI. So I'm going to start off with the AZ group command to go and create a new resource group. So this is a blank subscription here. There's no machine learning anything here, and so I'm just going to create this. Let's call it RG-DP-100-labs. So similar to what we did in the GUI interface earlier. And we give it a location, if I can spell it okay. And so let's just put this in East US. And so this should create very quickly because it's just a resource group. And we're going to need the resource group so we have somewhere to create the machine learning workspace. So the command I'm going to use now is azml space workspace create. And when we add the ML extension, it gives us the ability to do AZML commands, right? So it adds that part of it. So let's give it a name here for our workspace. Let's call this DP-100 demos, like we did in the previous video. Let's just do demo. And we need to specify what group we're going to put this in. So in this case, it's the resource group we just created. And because we didn't add anything else to the command, it's going to just default a lot of the things. So remember that we still have all those services that we need with the storage. We have the storage account, you can see being provisioned here, but we also have the Key Vault, we have the App Insights, and the container registry was optional. So we're just going to get the required stuff. And it's just going to match our name and do that. Now, I could have added all of this to the command. I could have went in and said Azure ML workspace and added the different parameters to be more specific with what I want to happen or if it's existing. But I'm just going to keep it simple and just use the defaults for this one. So that's going to take a little bit to create, similar to creating it in the graphical interface in the GUI. We just need all these services to go through. So let's let that happen. That's going to take a minute or two. So now we can see that we're onto the Log Analytics workspace being created. The Log Analytics workspace, by the way, is the App Insights, right, service that we see it in the other interface, and now it's we see the Key Vault. Right? And the Log Analytics workspace, is really the one that's behind the App Insights service. So just to be a little clearer on that, both of them are kind of required there. And then lastly, we see the Azure ML workspace being created. All right, there we go. So now that this is created, we can go and look at it in the portal interface. Let's pull that down a little bit. We can see our resource group, and with that we see our other services, but right there we see our machine learning workspace, right, with everything else. Now, once that's created, things don't stop there. We can do a little bit more with the command line interface, the CLI here. So let's do another one where we're going to create some compute. Now, this compute, not just a general virtual machine in Azure, this is going to be AZ space ML. So we're creating compute in the machine learning workspace. So let's give that a name. So we'll just say Neil's Compute. We'll give it a size. Now, one of the things about the sizes, you may be wondering, well, how do we know what size they are? These are standard sizes in Azure. So what sizes are supported with their compute instance? We could just look that up, and we would tend to be somewhat familiar with them. We want to give it a type as well. So what type of compute are we doing? This is going to be a compute instance. We need to specify what workspace we're using. So this is our DP-100 demo workspace that we just created. And we need to just tell it what resource group it belongs to as part of the command. So that's going to be RG DP-100 Labs. And at this point, this will run off and create a new compute instance in that. So the point is, while this is running, is that we can use these CLI commands to go and provision these resources and everything in our workspace. So, create the workspace, create all the resources, and really drive managing. It's going to be great for, that CI/CD type ML ops workflow type stuff, right? So, all right, this is going to take a tiny bit to run. So let's wait for that to happen. For those of you that are watching the recorded version of this course, we've sped up some of the video to save you some time. The typical wait for this can be much longer in real life. There we go. All right, so that's complete. So that's, again, off into our machine learning workspace, already done. You see the state is running, so all good. All right, let's do something similar. Now I'm cheating a little bit. I've actually just copy and paste the same command, but what I'm going to do is I'm going to change a couple things. So we're going to make some more compute. I'm going to change the name here to be AML cluster. And one of the big differences I'm going to make is that this is no longer going to be of type compute instance. I'm going to change this to be AML compute. And what that's going to do is create the machine learning compute cluster instead. So we do need another parameter in here. So the maximum number of instances, we're going to set that to 2. That way it's going to help control our costs. So it won't scale up to a really large number or anything. And let's get that creating. Now this actually creates a little bit faster, and the reason is because the clusters are shut down. So this is really like a definition that's being deployed. These don't really get created until we click the run button. It's really when we have a job going against it and it spins up. And so it's not creating the compute instance, not the same as creating the compute instance where it's creating a lot more that needs to be running, for example, possibly running all the time. This is really much more like on-demand compute. So this shouldn't take too long for that. There we go. So a lot quicker than the other one. We now have a compute cluster in our machine learning as well. All right, let's put this away. And let's go over to our machine learning workspace. So we're going to go into the studio view for this. Let's just close some of these up. You see that our compute was created, so we do get a notification in here as well. And so let's come down to our compute. Yeah. And let's take a closer look at the Niels compute. This is the compute instance that we did. And just so you know, the compute cluster was created as well, so it is there. So on the compute instance, when we're talking about doing command line stuff in here, we can use this compute instance to do a lot of the work in machine learning space as well. So we can manipulate file. We can use it to manipulate files and everything. So working with it. Now, there's a little sort of hidden bit with it, though. If we want to really access this compute, so you notice that on the right-hand side, there's a number of applications over here, right? So this is how we can communicate with it. So we have like the Jupyter Lab, Jupyter, interface, working with it with like VS Code and everything. But if you come over just a little bit to the right, so they're all listed here. This is where it's, all right, so you see them all. A little further to the right there. If we expand that, we see that there's actually a little bit more, and the two that we want to probably work with would be Terminal and Notebook. And so we can actually use these, again, you think run commands. It's going to run within that compute, but we can do it to do command line stuff. So I just opened up the terminal session, and you'll notice that it is logged into the Niels compute instance, and I can start running commands here. Now, this will have access to files and everything in the machine learning workspace. So if I want to run a script, for example, I absolutely can. So for, just to show, we can do a pip install. And one of the things about this, so when we're talking about this environment, we talked about the Azure AI ML library. So it's just going to make sure that it's not installed. So we're going to remove it, and then we're going to do a pip install of the Azure AI ML library for this. And just to sort of show a point here is that when we do this, now once this library is installed, I can turn around and run commands, right, against that library in Python, right? So think the Python SDK. This is how we're going to get that really set up here. All right, so that's all there, and since it's there, now we can start really taking advantage of whichever version of the Python SDK we just installed. So one of the main things that we like to do with all of that would be to run notebooks, right? Let's just clean this up a little bit. I'm just going to grab a command here. So to show you the notebooks, I'm going to do a git clone command. And what's interesting about this is even though it's running within this compute instance, which is essentially a virtual machine, it's actually going to be using the storage that we have mapped to our workspace. And so this is going to pull down everything from it works. By the way, this repository that I'm using actually has a bunch of these notebooks that I'm going to be using to demonstrate a lot of the stuff in this course. So if you want to use this same repository, you can pull it down and use it as well. So all right, now that that's there, you notice that I can refresh the files and I see what I just pulled down, right, with the git clone command. And so I have all these notebooks, from these labs that we have with our DP-100 course. We have a lot of content out online in general. So once we open up the notebook, a standard notebook interface in here, all right, so we can do things like, run a training script, whichever one we want to really do. We're going to be working with notebooks kind of throughout the course, so we're not going to explain, all the details of this one, just yet. And but you can see it's a standard notebook, so there's nothing really that special about it in here. Notebooks are just awesome generally, but it is going to be backed with the Python SDK because it's running in the compute. We need to attach it to compute, so it's going to run in that compute that we just provisioned, for that. And we can, if we have access to multiple compute instances, we do want to make sure we're connecting the right one. Now, you notice I just hit the authenticate button. When we first open up a notebook, it does need to be authenticated against that compute, right? Sorry, not the compute, but I mean the Azure, right? Against Azure. So when we're doing anything in here, making sure that the notebook, in fact, the Python SDK has been authenticated over to the Azure interface so it can communicate with our machine learning interface. We made that improvement so it's a little easier to just hit the authenticate button. All right, so I'm running some stuff here and just show you that we're going to get down to using the Python SDK, right? And so I just ran like the whole notebook in here. And this spawned a job. So now that we've authenticated all this stuff, it works, right? We can communicate to the machine learning service just fine with that. All right. So that first command, just so you know, is just making sure that we have the Azure AI ML library already installed, right? And that's one of the things that we installed a minute ago. And we can see what version it is and all that good stuff. And it works. All right, let's get back to some content and talk about some more stuff. Of course, we really can't do anything with building models unless we have access to the data. In this section, we're going to look at how to configure those connections to our data using URIs, which are Uniform Resource Identifiers. We'll also look at how to configure data stores and data assets and why we use them in our Azure Machine Learning Service. Let's get started with URIs. URIs are references to the location of your data. This will always start with the protocol of the service that we're connecting to. So for example, we would use HTTPS to connect to an Azure storage account, or maybe an external public location. When we're connecting to Azure Data Lake Storage, we would use the ABFSS protocol, which stands for Azure Blob File System Secure, which allows us to take advantage of the additional features of Azure Data Lake Storage. And if we're connecting to the Azure ML data store, we would use Azure ML at the beginning of our URI. One thing worth mentioning here is that by storing the connection information to URIs, as well as data stores and data assets within the service, we can avoid having connection information in our code like within a notebook. Although we can connect to data assets using a URI, in most cases, it's better to use a data store. The reason being is because data stores can encapsulate the connection information to the data. That way we can better protect the data, since the data scientist that would be using the connection within things like notebooks wouldn't need to have the connection information. The other reason for this is just that it makes everything much easier, since we can connect to a data store more easily, especially if we're using the same data store over and over again. There are also 4 built-in data stores that are created when you first create the machine learning service. 2 of these connect to Azure Blob storage containers, and 2 of them connect to Azure Storage file shares. All 4 of them connect to the storage account that was created or assigned when we first created the service. These 4 built-in data stores are primarily used by the Azure Machine Learning Service to store system information such as its metadata. It's important to realize that data stores just point to a data location, but they don't define any of the details of the data that you'd be working with. For that, we use data assets. Data assets can go a step further than data stores by providing specific information to the actual data. For example, we might build a data asset that points to a data store that provides the connection information and the overall location of that data. But then we can use a data asset to go further in specifying the specific location, such as a folder, that the data lives in, as well as the type of data that's being stored there. This way we have the ability to use a data store to store multiple types of data, and we have multiple data assets that can point to multiple locations with different types of data in that one store. For example, maybe one data asset is sales information, and another data asset is customer information. And both of those assets could be stored within the same data store where it's actually physically stored. Data assets will point to either a URI file, which represents a path to a specific file, a URI folder, which represents a path to an entire folder, or we can create a data asset that points to what's called an ML table, which represents a machine learning table. ML tables are basically a file or folder path, but it also has the schema definition with it, so that the machine learning service can read that data as tabular data right away. Data assets also support versioning because, as we all know, things change over time. All right, let's head over to the Azure Machine Learning Studio, and we'll see how to work with data stores and data assets. All right, so let's look more at the data. So let's start off. Let's go over to the resource groups and see our resources here in Azure. So back into our resource group. And this is the resource group where we have our Azure Machine Learning workspace. But notice that we have our storage account that it's connected to, but it is external to what we're doing. So let's open that up. And inside of here, this storage accounts are very ubiquitous across Azure. We use them all over the place for all kinds of different things. And so we have things like containers and file shares and queues and tables. And our interest is really going to be containers and file shares. So we'll look at containers here in a second, right? But file shares are right below that. And so we do have a storage browser as well. So it's a little easier to kind of look to see what's in here. And with this one, let's just take a quick peek at the blob containers that already exist in it. And I just wanted to point out that there's a number of things that are already here. So you see the some things there. You see under the file shares, a couple things that are already there as well. So when we provision this, the Azure Machine Learning Service really provisioned all of these pieces. All right, let's go back. Let's take a look at what we see in the Machine Learning Service. So let's open this up. And of course, we're going to jump to the Studio. So switch interfaces here. And let's come down to data, right? So let's get rid of that. So I mentioned before, we're talking about data stores, data assets and data stores all the time. So let's go over to data stores, and there's 4 data stores that come provisioned with a service. So this the workspace working directory here happens to be an Azure file share. This is what we were basically looking at. So this is the name locally here, and we have the artifact store, the file store, and a blob store, right? And this is the default storage. Notice it's marked to default, but all of these are from the storage account that I just showed. So even though the names seem a little bit different, these are actually pointing to those different, the blob containers and the file shares from that storage. So it is possible to go back here and play with it. So for example, if we wanted to go and do a brand new container in here, we absolutely could. Storage can contain a lot of content. So let's call this new container training data and go ahead and create that. And then, later on, we could use this container to actually store data afterwards. So if we're we have training data, anything like that, we can store it. We can actually use it from the machine learning workspace. All right. So now one of the things that we're going to need in a little bit, and something I want to show you, is I want to have the access. I need the access keys to this, and you'll see why in a little bit. So let me just copy these. So I'm going to grab the storage account name. I'm also going to go and grab the key for this, right? So I'm just going to use access keys. Ideally, we do this with like identities, and there's a way to do that, but it's much more complicated to show. So, I'm going to cheat a little bit and just use one of these keys. So I'm just going to record this quickly. All right, now at this point, there we go. I almost forgot to paste that. So just putting them on another screen. So at this point, if we go back into our studio, the idea here is that I can create another data store that points to that container that we just had. So let me come down and grab a notebook, one that's already set up for me. The last thing you want to see is me to type in an entire notebook. So a couple things we're just going to do for the plumbing. We want to make sure that the Azure AI ML library is there, so make sure it is installed. So that's all good. We're going to connect to the workspace. This is going to make sure that our credentials are already verified for this notebook to talk to the Azure Machine Learning Workspace. So that went okay. And then this one, we want to make sure that we have this ML client, right? So this is something that we use a lot in the Azure Machine Learning Workspace, and pulls up the configuration for everything. So we just have this ML client object that we can use. Now, once we have that, we'll tend to use this object to work with the machine learning workspace. And in this case, we're going to be playing with data stores, right? So it's important to understand a lot of the machine learning environment to work with these spaces. So this one, we're just going to list it. So let me just run that. And we see currently we have the 4 data stores that we showed earlier in the portal interface, right? All right, so the plan though is that we want to create a new data store. And if you remember, data stores are going to be basically like connections over to storage somewhere. So it's not the specifics of getting to the file, it's like where it is and how do we get access kind of to the general storage, wherever that is. And so this one, there's a little blurb in here to create a new Azure Blob-based data store, and just going to pop in the account name and the account key that I copied earlier. And just while I'm doing that, if you look at the code here, you'll see that we're giving this blob data store a name. Let me copy that. Yes, we can copy. We're giving it a name. We're also pointing it to a specific container name. That's the training data container that I just made a minute ago. right? So the name of the blob in the data store can actually be different than the actual name of like the container or the folder or whatever that we're pointing to. Last thing we need is we need the account key. Normally I'd say, don't copy my key, but I'm going to delete all this in a minute anyway, so I wouldn't worry about it. And let's get that creating. Right, so this goes fairly fast because it's just the like connection type information. So that was successful. Now if we go back and we list our data stores again, we can see that we now have the blob training data that points to that container that I just created. All right, so that works. Now, the next part, actually, let me go over and show you the data stores right here. So you can see that it shows up in the data stores tab as well. I almost forgot to show that. So the next part we want to do is look at creating a data asset. Now the data asset is really the connection to that specific file or folder. So we can go to a specific file, to a specific folder. We can connect to an ML table, right? So we'll talk a little more about that. And this is going to use a data store. You know, typically it uses a data store to kind of get connected. It doesn't have to though. So in this one, we see that we're just setting up a path. Say there's my data. The asset type is going to be a URI file. So it's like, yep, direct connection to a file. We're going to give it a name. And this is just going to be in the like the default store here. So we could run this, right, and get that connection over to the diabetes data. So at the very bottom of that, of course, and by the way, yeah, this is when we create this. I should mention this. This is going to be like uploaded to the default data store. I said it was just in it, but it's actually uploaded. Just misspoke a little bit. So yeah, so there it is. We also get a new path. So if we're looking at a path like to HTTP or anything like that, we do get a new path to it. It's now part of the Azure ML space as a data asset. All right, next one, let's go to URI folder. And this is going to be very similar, but in this case, we're going to point it to the blob training data folder that we created earlier. This was just a folder. And so because it's a data asset, it starts with the Azure ML name. There's the path to what we want. We need to make sure that it's marked as URI folder. And that's good to go. So we just create that. And I think this is a pretty good combination of showing a data asset with the data store with the data asset together to say that's where it is. These are the details of like what folder, what file that we want. And now it's an object that we can use in the machine learning service. All right, the last one. The last one we're going to do is to create an ML table, right? Now, earlier we talked about ML tables. This is where we have an ML table definition. So let me come over here and just show you a little bit of that. So just up into so from there, it's going to be just under the data. And notice there's an ML, not just the data, but there's an ML table file right there with it. So we need both of those to really support this one. And again, the ML table is it stores the schema in there. So so that right there is going to store the schema for this. It's going to describe it. So let's run this, and we're really getting another data asset with the name diabetes table, but it is of type ML table. And there's a lot of services that actually, a lot of different features in the machine learning service that actually require that. All right, now let's look at our list of data. You know, here it's listed as data sets. In the interface, it's data assets. Same thing. And we see that, you know, diabetes local, the data store path, and the table are all there. All right. So something like the ML table, we can read it, and notice it just gets easy to read because we just refer to the Azure ML space and say, hey, what's the ID? There's the data asset and the ID for it. In this case, we want to get the one for the diabetes table. And so That's the registered data asset that we're using in here. But notice the protocol is just Azure ML, basically saying it's the local one in the machine learning service, right? In this case, a data asset. So let's run this, and we see that we should hopefully get some data returned. Okay. All right, there we go. So we had a table put out as a pandas data frame, and it looks pretty good. Now, of course, when we're doing, the reason we set up all the data is because we want to use this all over the place in the machine learning space. So we can use this in a job, for example, and work with it. So those data assets, right? All of these become a lot easier to use, right? Because now we can use them basically by name. We don't have to worry about the connection information, all that stuff in the notebook. All right, with that, I think that's a pretty good overview. So let's jump back into some content, and let's talk a little bit more about next up is going to be compute. All right, let's talk about compute. Compute is one of the most important resources that we use within our service, since we really can't do anything with the data without using compute. The overall challenge here is to make sure that we're using compute efficiently. The main reason is because this is one of the most expensive resources that we use. But also, specifically for larger scale projects, we also want to get our data processed and our models trained in a timely manner. So let's take a look at how to configure compute within our workspace. Within the Azure Machine Learning Service, we use seven different types of compute. Here on the slide, we can see how these different types align with the machine learning task that would use it for, within the workspace. So let's talk about the different types. Compute instances and serverless Spark are used to back notebooks so that when we're executing code in the notebook, the code will actually be executing within one of these compute environments. This aligns with doing experimentation in the machine learning process. A compute instance is essentially just a single virtual machine. These are assigned to individual users. Serverless Spark is a newer feature of the Azure Machine Learning environment that lets us perform Spark-based workloads, such as running notebooks, more efficiently. And as an added bonus, we don't have to configure the compute environment for it like we would to create a compute instance. However, serverless Spark compute does have some disadvantages. For example, it only supports in-memory SQL, Spark SQL. So there's no support for Metastore-based tables or databases. We can't consume any linked services that we would have in the Azure Machine Learning Service. It also doesn't support pool-level configuration or library management. So if any of these restrictions would affect your use case, you can simply go over to the compute instance instead, since you're given full control over the compute environment with that one. Moving into the middle of the slide, we see compute clusters, serverless compute, and Kubernetes clusters under the machine learning activities of model training and running pipeline jobs. A compute cluster is similar to a compute instance where you have full control over the configuration, but what's different is that this is a multi-node cluster of virtual machines that can scale as needed. This makes sense considering model training is typically done with larger amounts of data. And by using a multi-node environment that can scale and take advantage of parallel processing, we can process our data much faster. We can also use serverless compute to accomplish the tasks of doing model training or doing pipeline jobs. Similar to serverless Spark compute, this compute is also a fully managed on-demand style of compute that you can use for training jobs. In other words, there's really nothing to configure for this. We can just use it, and similar to a compute cluster, the serverless compute environment will scale as needed to do the work. This can be a great advantage to minimize the amount of operational overhead that you might need to do. As well, another great advantage is we can specify the size of the compute that we need at runtime, rather than having a specific configuration, like we would with a compute cluster. And one of my favorite features is that if we have a second job that's starting, it would get a new node or another cluster to start running the job. So we would have both jobs running in parallel. Whereas if we were using a single compute cluster, the second job would be queued behind the first job. Next, we have Kubernetes clusters. Later, when we discuss environments, we'll see that Docker containers are typically used to specify the environment. So it makes sense that we could leverage a Kubernetes cluster to provide parallel compute by hosting the Spark-based cluster by running multiple container nodes in the Kubernetes cluster. What's interesting about this compute is, first, it gives you a lot of control over the environment, including the ability to host many different types of workloads in the same Kubernetes cluster. It also has a second advantage that can be useful to connect to an Arc-based Kubernetes cluster, so that we could potentially connect to a Kubernetes cluster that is on-prem and use that to provide the compute. Next, we have attached compute near the bottom of the slide. You notice that it covers doing experimentation, training, and doing pipeline jobs. The reason for this is because attached compute allows us to connect to existing compute in Azure, such as an existing virtual machine or an Azure Databricks cluster that is outside of our machine learning workspace. The typical reason we might use this is because we may have been doing machine learning or data engineering workloads outside of the machine learning workspace, before maybe it was even created, and we already have that compute existing. One example might be that we're using Azure Databricks for a while, and instead of creating duplicate compute, we simply attach to the existing compute. Lastly, on the right-hand side of the slide, we have containers, which can be used to package our models when we deploy it to a real-time endpoint, where we can host the container a few different ways. We'll be looking at deployments later on in the course. With that, let's jump into a demo and see how we configure compute. All right, let's talk about compute. So earlier we saw the data that we were using before. All right, now you can't really do anything with the data until we have compute to really go with it. So one of the things I'm going to do, I'm going to use this in just a minute, is I want to go make a small little file. You'll see why a little bit later. There's this compute setup shell script that I made, right? And I previously made it, so I'm just going to use it again. So right in here, it's just a git clone command. Right, just so you know what's in this. You're going to see this a little bit later when I go to create the actual compute. So it's just pulling that down. Again, that's the repository that we have all of these notebooks and everything that I've been playing with. So feel free to go and clone that if you want to on your own environment. All right, so that's there. So let's come down to compute, and what we're going to do is. This time we're going to use the interface for this. We're going to make a brand new instance of for compute. So let's do new here. And just give it that a second. It just needs to refresh. Let's give it a name. So how about Neil's demo compute? And here is just what type we want. We have the what size. So I just grab the standard DS11. So there's a bunch of recommended sizes here, but we can play around with this. You can see the pricing, a lot of different things about this. This is going to be a choice that you need to kind of sit down and think about a little bit. How big do you want this to be? Because the bigger, the faster. If it's GPU, for example, it's going to be more expensive. But at the same time, we're also probably running through a lot of data. For doing experimentation, for example. So that's it's up to you. All right, next page, scheduling. This is, I think, probably the most important feature that we really have here. This enable idle shutdown. So shutdown after, in this case, 60 minutes for the default. So if a data scientist walks away from this compute, if it's idle for that long, it's going to shut down after an hour. Now, what what number should you have here? It depends. If you have it for something like 5 minutes, if they run for a coffee, it's going to shut down. When they come back, they're going to be mad because they got to wait for it to start up again. So something that's reasonable, but at the same time is helping to minimize the costs that are associated with everything. So you can change that if you like. Right. Another thing in here too is it is possible to create a schedule that you can start and stop the virtual machines on a particular schedule. I've had customers that say, for a data scientist, instead of using that shutdown time, we actually just set a schedule to say, from 8 a.m. to 5 p.m. we do that, but that's up to you. All right, next up, security. So this one, we can assign this to another user. So if I'm more of a compute operator, I can create this, set all the right settings, and assign it to a data scientist if I want. There's also things like managed identity. There's managing on a virtual network. As a data scientist, this is going to be probably outside the scope of everything, so we're just going to skip over that. All right, next up, applications. It is possible to add applications into this compute instance. In this example, you notice in the setup scripts, there's two setup scripts that we really have. There's a creation script in here, as well as a startup script right below that. So the creation script is going to be when we first create the virtual machine. Basically now, this script will go and run and help create the machine. The startup script is going to run every time the machine starts up. So whenever it stops and then starts again, that script would run over and over again. So in this case, right, instead of using that startup script, if you remember that shell command that I had, that was actually a creation script. So once we do the get clone, it's like a one and done, right? So let's actually configure this to do our get clone. Now I already have a file for it, so it's just a matter of me pointing to the file. Say, yep, there's the compute setup that we made. That's why I showed you this earlier. And we could pass any arguments, anything like that. There's a timeout setting for it. And that's all we really need to do to say, when you create this, here's the all of the commands I want to run for that. So let's move to the next page. There's really not too much to this to provision it. Next page is just tags, which we do for all kinds of resources, and then we review it. All right, and let it go create. That's it. That's it. So pretty easy to work with. And then we have another compute instance that we can kind of work with within our workspace. All right, so that's going to take a tiny bit to go and create. So while that's going, let's talk about compute clusters. Right, so that's another tab in here, and it's possible to do this with the interface as well. Just make a new one. Very similar process. However, just to change things up a little bit, let's do this maybe with, how about we do this with the Python SDK, right? So let's go over and use a notebook for this, just so we can see it done a slightly different way. And it should be this one, yeah, create a compute cluster. All right. So what's happening in this one, right? The compute cluster. Actually, let me go back, make sure some plumbing is done first. Make sure that's all usually done fine with these notebooks and machine learning, but we do need to make sure our credentials are done. And it's really the next one that we want to make sure we have the ML client, because that gets used in a lot of the script, a lot of the cells later on. All right, once we do that, so going back to the create a compute cluster, this is an example of doing this in code in the Python SDK. So we need to import AML compute. We're going to give it a name, right? So the name assigned to it, so AML cluster in this case. If we already have one, it's just going to really update it, right? So, or say, hey, it's already there, and I believe I already have one in this case. So we'll see in a second, but this is much more about the script. So let's talk about that. When we make a new AML compute object, we're going to specify what type it is. It's going to be AML compute. So that's our cluster. We're going to give it a size. We can set the settings like min instances, so the minimum number of instances when no jobs are running. We like 0. a lot of the times. Max instances equal to 2, so it'll only scale to 2 nodes. And then the idle timeout before scaling down. So clusters are really much more on demand. So in this case, it'll be 0. When a job is scheduled to run against it, it's going to spin up. But then once the job's done, it's going to be 2 minutes before it starts shutting. It shuts itself down. And then we also have dedicated or low priority. So you see this one is set to a dedicated tier. The big difference here is that low priority is when we have extra capacity in our data centers, right, really in our regions, we will put compute on sale. And so it can be at a bigger discount. It's kind of prorated for how much capacity we have, spare. But the catch is if we start running low on the spare capacity, because we budget for a lot of it, we might take that back. And so that's why there's a little note there that there's a chance of job termination here, because we may actually preempt these machines. So if you have a workload that you really need to be done, you're going to want to leave this as dedicated, for this. If it's something that's a little more nice to have, then maybe we use a low priority to get those savings. All right. So this one we'll leave at dedicated, so we have it. And then the last thing, of course, is just we're going to do the begin create or update command to get this compute going. So let's go and run this. Let's come up to the top here, give that a run. And you notice in this case, I happen to already have a cluster named that, so it's just going to reuse it. But if I didn't, that would have spawned and created everything that we just specified, so that works okay. Now, once we do have one, though, we can modify it. Now, if you recall, the code just above this already had the max instances set to 2, so we could change if we like, but I think you get the point, is that we can really say, hey, using the AML compute, specifically this named compute, here is the change I want to make, right? So we can update these values like the max instance, because it's begin create or update, it's update. So when I run that, we get, that's going to go over and configure that. So that's not really a change in this one, but theoretically it absolutely could be. All right, as well, we can view these values. So if we get a specific compute cluster, we can pull off any of the values, like you see the name and the max instances here being outputted as a string, so maximum 2 nodes. All right, next up, now this is going to be a little bit bigger. So this is, without really getting into the details of it, this is a training script, and this cell is going to write this out as a Py file. So we have everything we want to do in here. So it's scikit learn, and it's going to do basically train them all and all that stuff. So we ran that. That wrote out a file. Now, the reason we did that is really to show this next part. So that file is going to get used as a command in a command job against the compute that we just defined, right? So all of this together is going to get to do that. So this one will run. We'll talk about jobs and everything later on, but the point is that we now have a job that was submitted. That compute cluster is actually going to spin up to take care of the job, so the job will be waiting, and then we can sit and monitor it to see how that's going. So that's actually just at the bottom of the output down at the very bottom here. So you can sit and wait. Now, one thing about this is that it typically takes a number of minutes for that compute cluster to spin up, and then we can start using it. All right. So I think we're pretty good here. Why don't we go back to some content and talk a little more about what's up next. Just to wrap up this section, remember that compute instances can only be assigned to one user. A common practice is to have people assigned to the Azure ML compute operators role that create compute instances and then assign it to the appropriate data scientist. Another best practice is to review your compute settings to ensure that we are minimizing compute time and just overall being efficient. So when it comes to a compute instance, we can manually start and stop it, but if a data scientist forgets to stop it, we might be incurring a lot of additional costs that we don't want. So to avoid that, we could schedule the compute instance to start and stop at specific times, or, and I think this is the better option, we can configure the compute instance to shut down after a specific amount of inactivity. One of the challenges when doing machine learning in general is to control the environment. What I mean by that is when we're doing something like model training, are we being consistent with the different packages, libraries, and dependencies that we're using to do the data transformations or model training? This is what defining an environment in the Azure Machine Workspace is all about. An environment is used to define the context, and what I mean by that is everything about the environment, such as packages, libraries, and dependencies, that we want to use to run our workloads, such as model training. By using an environment, we can be consistent in the configuration of performing the same task repeatedly. When we create an environment, we're actually creating a definition for a Docker container. The Azure Machine Learning Workspace comes with a number of curated environments, basically pre-configured environments that we can just use, assuming that it has the configuration that we need. Or we can also create a custom environment where we get control over what is being loaded into that container. When we create a custom environment, we're really just configuring a new Docker image. So we can do this by using a Docker file to specify the configuration, or we can use conda YAML files to define the configuration as well. Both of these options can give you full control over exactly how the environment is being configured. Let's take a closer look at using environments in the Azure Machine Learning Workspace with a demo. Let's go. All right, so let's look at environments in the portal here. So environments are used to really, provide that well, as it says, environment, and when we're running like things like jobs and whatnot, say this is the setup that we really use. And so we have curated environments, and then we have custom environments. So curated environments are ones they're already built, right? These are kind of out of the box. We have a number of different configurations for them, and so you can browse through this list, or probably even easier is just simply search. And so let's do a search for maybe like something like TensorFlow, and we'll see that it will filter down to some environments. And this also picks up on tags as well. So you can see that these are actually tagged with TensorFlow as well. So a search is actually usually pretty good for all these. And the source of on these are all listed as Azure ML. Okay, so these exist, right? And as long as we know that which one we want to use, we can test it. It's just really fast to go and grab one of these because we can refer to them. We can do custom environments as well, though. And this is where you're going to get a lot more control over what's in there. You can do this in the GUI interface. I'm going to show you this in a notebook instead. But it's kind of a yes, you can. You can go through and create it, specify what packages and everything you want installed. All that configuration is going to be pretty good. But the easiest one is definitely curated environments. That's probably going to work in most cases because if you know which library you're really using, like scikit-learn or TensorFlow in the version, you could probably find one of the environments to work with that. Okay, so let's go over to a notebook and see how to work with this a little bit more. So just a little bit of plumbing that make sure it's all there. We get the notebook kind of connected as well. So let me come down and do that. Right, and again, the ML client. So I forgot I ran all that, so it's all good. So run a script as a job. So this is going to write out a training script again. And so we have everything in here. I'm just going to run it. We'll talk a little more about training scripts later on. But the point is that this training script is going to be used within a job. So similar to the last demo that we did, this is going to create a command job. It's going to point to the source directory and then specifically run the Python command on that Py file we just wrote out. Now here's what we're really talking about. So the environment that this is going to use, it's the Azure ML, scikit-learn 0.24, etc. It's this curated environment for it, and we're gonna use that environment against that compute. So how does that kind of work, right? Isn't the configuration part of the compute? Well, the environment is really a Docker image that's going to run with that. So, so that's really just curated, Docker images for it, and so we can take that, we could submit it. All right, so let's go do that, and it's going to run that Python file within that environment. Okay, so we can also list all the environments, and these are going to be all the environments that we have. You'll notice that when we list them, that there's these will have this Azure ML at the beginning of it. So right here, anything with Azure ML dash in front of it is a curated environment, right? So a lot of the common environments that we typically see are going to be listed here. So PyTorch, etc. there. All right, so pretty good list, I think, for most cases. But again, if it doesn't work for you, you can make your own. So you can retrieve one of these environments if you want to take a closer look at it, right? Let me just fix a little typo there. There we go. So so we can pull one of these environments, see the tags, see the description. We can do all of that programmatically if we like to. All right. But as I keep saying, if it doesn't work for you, if the curated environments don't work for you, we can go and use a custom environment instead. All right, so how do we do that? This is basically just a Docker image. So you'll notice that the environment that we're creating is based on a Docker image that's already existing. So wherever you want to kind of use as a base, we're going to give it a name and a description, and create this. Now, in this case, this is very simple. We could go a lot further and say, well, let's build a new Docker image that we pull from our own repository and do all that. But we'll keep it simple. Let's just run this, and we'll get a this environment is now created, right? So let's go and see that get used. All right, so you notice that up here, the name, just a reminder, it's Docker image example. So coming down to this next block, notice the name of the environment, Docker image example, and then basically what version it is, right? So :1, and that's good. And this is just running another job, right? But this is going to use that Docker environment instead. Okay, so that works, right? This job is now submitted, it's off to run, and it should be just fine. So just a reminder, we can build these, to have a lot more in them. So it's really, you get the control over that Docker image, however you want to manage those. Okay, with that, let's jump back over to some content and wrap up this video. This concludes this video, where we covered a lot of the core configuration of the Azure Machine Learning Workspace, starting with introducing its resources and assets, showing you how you could work with the workspace using the Python SDK or Azure CLI, and then we discussed making data available to the machine learning workspace. How to configure compute and the different options there. And we finished up with introducing environments and what they represent in an Azure Machine Learning Workspace. I hope that this video has been useful to you, and I hope that we see you again as you continue on through this training series. Thank you for watching. Hi there, my name is Neil McIsaac, and I'm a Microsoft Technical Trainer. In this video, we'll be focusing on running experiments using automated machine learning. We'll start this session by introducing what automated machine learning is, followed by how to find the best model using it. We'll also spend some time on introducing ML flow and how it can help with tracking and managing your experiments. So let's get started with what automated machine learning is all about. One of the biggest challenges with doing machine learning is deciding on which algorithm, as well as all of the best values for our hyperparameters that will give us the best model. Typically, Data scientists are going to spend a lot of time choosing and configuring algorithms, then train a specific model using those settings, and then spend time evaluating the performance of the model. And then, after all of that, repeat the process with maybe a different algorithm with different settings to see if they can improve on the model performance. Essentially, there's a lot of trial and error in the overall process. Now, to give all the data scientists out there credit, their knowledge and skills greatly reduces this process, but there's still a lot of trial and error overall. So, wouldn't it be nice if we could simply throw compute at the problem? In other words, what if we ran multiple experiments with different configurations, such as different algorithms and different settings, all at the same time, and we let the service evaluate the models that are built from each experiment run to determine the best model for our situation? That's exactly what automated machine learning does. In essence, we can kind of brute force the problem by running many experiments with different configurations all at the same time. And at the end of it, we can see which model performed the best and how it compared with the other models that were built. Then you might be thinking, well, what's the role of the data scientist in this case if the service can just determine the best model for us? Well, that's a great question. I would absolutely say that the data scientist is still very much needed with this process because there's still a lot of work to do. And their knowledge is needed to really get the most out of AutoML. And there's still a lot of tasks that AutoML can't do. So the benefit here, and this is true even if you're a data scientist, is that AutoML can reduce the time it takes for you to evaluate multiple experiments at the same time. That's assuming that the models that you're evaluating are supported in the AutoML service, which is likely since it supports a lot of the common algorithms that we typically use. AutoML supports algorithms in these 5 categories. Classification, which is used to predict a categorical value, for example, classifying support tickets into different categories like technical issues or billing inquiries or general questions. Regression, which is used to predict a numerical value from other values in the data set. For example, maybe to predict housing prices in a particular market. Time series forecasting, which is intended to predict future numerical values based on a time series of data. So the easy example on this one is stock market predictions. Computer vision, which is used to classify images and detect objects within images. And natural language processing, or NLP for short, which is used to do text classifications or named entity recognition, which is essentially to do processing of text. Within each of these categories, AutoML supports a number of specific algorithms that can be configured for experimentation. So how do we use it to find the best model? Let's look at using it to find the best classification model. Before we run any experiment, we need to prepare the data. The same is true if we want to run an AutoML experiment. So to get started, we need to create a data asset in our workspace, but more specifically, it needs to be an ML table. If you recall, ML tables store the schema for your data in an ML table file and can provide the data in a tabular format by using that schema definition. On the slide here, you can see an example of specifying the ML table in a Python script by setting the type parameter to ML table and specifying the path to the data asset that we're using. Part of preparing our data for processing involves configuring scaling and normalization to help provide the best data to train our models with. Scaling and normalization help to balance the weight of different features, so we don't have any large-scale features dominating the training. AutoML will automatically apply a number of scaling normalization techniques to the data for you. There are also a number of featureization settings that you can configure for AutoML to automatically apply to the data, such as imputation for missing values, categorical encoding, which is used to convert text categories into numbers, automatically dropping high cardinality features such as row IDs and feature engineering, such as separating date-time features into the individual date part features. One of the bits of feedback that I often get about these settings is that many data scientists feel that they don't have as much control over the data since we're really letting the AutoML service determine most of it, and we have very limited control over those settings. Basically, our control is mainly limited to enabling or disabling those transformations on specific columns. However, remember that before we do any experimentation, we need to prepare our data first. So if you want more control over these transformations, just do them before we pass the data to AutoML for processing. Essentially, this is the exact same process that we would do if we were doing our experiment much more manually. All right. With that, let's move over to the portal and see how to create an AutoML experiment. All right, so let's start off with going over to the automated ML page here. And what we're going to do is we're going to set one of these jobs up completely within the GUI. So we're going to start off with a new automated ML job. And this is definitely one of the easiest ways to approach this, even though usually we'd do this with a script. So let's give this a name. And I'm going to keep this simple, so we'll just keep the new experiment name as default. We'll put a description in here. The thing about this is just we want to show what this does, right? So we hit next. We need to go and pick the data as well as the task type. So let's start with that. So this is going to use we have a choice of a bunch of them, but we're going to use the classification option here because we want to classify whether or not somebody has diabetes. We're going to use the diabetes training with this. So this is similar to the data that we've seen in previous data. So we have all kinds of data in here, the patient ID, pregnancies, things like BMI, all that stuff. All right, so we have data. We want to classify it. We're going to go next. And the next thing we're going to set up is we're going to start diving into some of the details of how we want this to behave. So what is the target column that we want to predict? In this case, we want to find out whether or not, predict whether or not somebody might have diabetes, whether they're diabetic or not. So that looks pretty good. And the next part, and this is part of the interface that it's almost it feels a little bit hidden. So I want to show where these are. So under the additional configuration settings, we can specify what metric we want to use as the primary metric on how we're going to rank all these models. So we can use like AUC weighted, accuracy, and it really depends on which category we're choosing previously. So in this case, because it was classification, we can do this. Next, we want the explain the best model. In this case, we also have the option to do ensemble learning, which is going to take multiple models and use them together to generate a model. So that's an option that we can play with as well. And we can this next part to a lot of people the first time seems a little confusing. So this is use all supported models, and then right below this we have a list of blocked models right here. And so this is saying, hey, use them all except for these models. So let's select a couple. Let's take maybe this is a pretty good list here. Let's take random forest, extreme random trees. Take decision tree. We'll just have the thing against trees, right? Maybe so something like that. And when we do this, it's going to use all the other algorithms except that. Now, what's interesting is we can reverse this. So we say don't use all of them, and then that changes to allowed models. And now this is going to be what we want to pick off the list. Say we want to use logistic regression. Let's take KNN and SVM and decision tree. So only these algorithms are going to get used in this case. So it's really up to us which way we're going to do this. I'm going to switch it back, and let's just open it up to everything in here. Okay, so a lot of the configurations about how this is going to behave. So it's not too bad here for what models we're going to use it. And as a data scientist, you can control that, of course. So let's save that. The next page we're going to look at is the featureization settings. So this is going to be how the automated ML feature is going to go through and actually play with the data. So first off, like the feature type. So for patient ID, for example, that is, has a really high cardinality. Probably shouldn't be here. We'll, as we run it, it can determine that. But the feature type is going to be, well, what type of data is it? Is it numeric? Is it date, time? What's going on here with it. So you just want to make sure that the service can actually recognize any of the columns for what it is. Now, imputation. If we have null values, how should we replace those? Is it do we use a median filled with a constant? And for these, I'm just going to leave everything set to auto. It actually does a pretty good job to determine a lot of these. So both of these are set to auto here, and we can do that for any of the columns that we're providing as our feature data coming in here. So not too bad. And we can see a data example for any of it too. So let's save that. And let's talk about limits. So on the task settings, we can place limits on everything. So the total number of trials, concurrent trials, the maximum nodes, things like the score threshold, any experiment iteration timeouts in there. And so that's going to really help us reduce the amount of compute that we're using. We don't really have to try and kill this with trying to test every single model. We also support this, early termination in here as well. So we find that trials just are not producing better results. We can say, stop, for them. And so this is all, again, it's automatic. We're really just doing some high-level looks at what we're picking, how much compute we want to spend on everything, and totally up to us. Now, of course, we want to validate our data, so we can do the validation. In this case, again, it's automatic, so it actually can work through that. But we can be more specific if we want to. And we can also specify what we're going to use for test data, right? So our test data, we can just do the typical train test split, where we take the data that we're providing and split it up and use it for testing, and then how much of a percentage we're going to use, right, from our training data as test data. So in this case, just leaving it at 10%. We can do it. All right, let's move on. Next. Compute. So once we configure all this, this is going to spawn a job with a lot of other jobs. We have a few different compute options here. The compute cluster is the one that is very typical because we're probably doing a lot of data. But the new one is serverless, right? This is really a really great option. And again, this is really like compute on demand. We can still configure this, right? CPU, dedicated, low priority, all of those settings. And this goes back to talking about compute. All these settings are really there to say this is how we want this to behave. So again, low priority is when we have compute on sale. Just remember that it is something that if we are low in the extra capacity in our data centers, then we may actually preempt the low priority. So it's a great discount, but question mark whether you can use it. So if you need this to absolutely run, leave it dedicated. With AutoML, it might be an opportunity to use low priority because we're just trying to figure out a lot of the beginning of our processing, of our model evaluations. All right, so once this is done, this is going to show up as a job, so I'm just making that go. Let's get rid of that. And do remember that this is going to be like a master job, a parent job that's going to go and spawn a bunch of child jobs in here. So we'll look at that later on. So that's submitted. This is going to spin off a whole bunch of jobs, figure out all those models, rank them, figure out what the best one is, and continue on. So, child jobs are listed here. This is just spinning up. So, we could, might be a little quick to go and jump in that right now, but eventually we could go see that, especially when it's done. Okay, let's do another one. In this case, we're going to show the Python SDK version of it. So I just jumped over to a notebook here really quick. And on this one, we're going to really do this pretty much the same process. We're just doing it in code. So this is everything to do with our data, our input data. And notice it's an ML table type. That is required for these. And so we have our training data. Moving down a little bit, we're going to create, right in here, it's an AutoML classification job. So right here, we see it's a classification job. And then the settings for it. So what do we want to name it? What is the primary metric? that we're trying to calculate for it, how we want to validate it. Do we want to enable that model explainability? That's going to be for that the winning model. We can set any of the limits on there on the job. So it's just setting a lot of properties, similar to what we saw in the interface. We can do that all right here. So number of trials, all of that stuff is in here. And then of course, setting the training, we can set the training up to like block certain algorithms or to enable certain algorithms compatibility. So it just comes back to what I was showing you in the interface to say this is what I want, how I want it to behave, and what's on the list to use and what's not on the list to use. Okay, that's all optional. So once we have all this, we can go. Let's queue this up to run. All right, so. Yeah, let's go run this. All right, so let's get that cell running. I was thinking I was forgetting something, and now we have a classification job that's being set. So this goes really fast because we haven't submitted it yet. So let's get that submitted as a job. Right, so there's our classification job. We're going to create or update the list of jobs using it, and then we're going to see the status URL on it. All right, that's all this code really does. So let's go run this. Now, do keep in mind that AutoML is going to be spawning all these jobs. So this is not a quick process, right? This is still the parent job that's listed here. It's going to run off, spawn that parent job. Things like featureization is going to be a child job. We're going to have a bunch more child jobs to do all the model training for everything. So right now, we really just need to sit back and wait. So while that's going, let's jump back over to some content and talk a little more about what's going on here with AutoML. So while our AutoML experiment is running, which can take a while, let's review the code that we used in the demo when we were using the Python SDK. In the code on this slide, we can create an AutoML job by configuring the type of model that we want to train models for. In this example, specifically, we can see the AutoML.classification function being configured to specify the compute, the name of the experiment of the training data, the target column name, which we're trying to predict, which metric we want to use to rank the models, which in this case will be accuracy, the number of cross-validations that we want to use to validate the models, and lastly, whether we want to enable the model explainability for the best model run. We can also set the limits for an AutoML experiment. This can help us to avoid wasting money on compute calculating models that likely won't produce better results. We're simply trying to help control our costs. In order to do this, we simply set some limits, which you can see an example of in the slide here using the Python SDK. In this example, we're using the setLimits function to set the parameters of the classification job that we specified on the previous slide, and we're setting the timeout minutes that the job will be limited to, which in this case is being set to 60 minutes. We're also setting the trial timeout minutes to be 20, which restricts the maximum number of minutes that a single trial will take. And we're limiting the maximum number of trials to be limited to 5. We're also setting the enable early termination property to be true, which will allow the AutoML process to end the experiment early if the score isn't improving in the short term. All of these settings can help us to restrict the amount of time being spent calculating the different models, which in turn helps us to limit the amount of compute that we're using. Once we configure all the settings for the AutoML job, including any of the limits we might place on the job, we can then submit the job using the Python SDK by calling the create or update method of the jobs class in the ML client. One thing to note here is that when we submit an AutoML job, that job is going to produce a number of child jobs. So each model that is going to be trained will be done within its own child job. So you can think of the AutoML job as being the master job that will spawn all of the child jobs. Also, the featureization process will also be done within its own child job. When the AutoML job completes, we can examine the job in the studio where we can see the winning algorithm with the other top models listed in the order of the metric that was used to rank the models. In this case, we can see that the winning algorithm was voting ensemble that achieved an accuracy rate of 0.953. And since it was the winning algorithm, and because we had the enable model explainability setting set to true, which happens to be the default, we can view the explanation of the model if we want to. So let's go back to our workspace and see the results of our AutoML job. Hopefully it's all finished. Let's see. All right, so now that everything's finished, actually not all of it's finished, so the two jobs that we spawned, we have one that's still running there. So you can see that the AutoML job that I did in the interface is still running, and that's because I didn't put any limits on it, my bad. It's just to say that, hey, it's gonna do a lot more. The other one that we did in code is completed because we actually limited the number of trials to, I think it was 5 when we created, so it's actually pretty small. So here we can see the parent job. I love the names, by the way. It's like, icy garlic. It's, under, they're just random names for it. And then below this, we see a bunch of the child jobs, including the one that was the best, right? Because that also had a job to explain it. And so you can examine any of these jobs when you go through it. They're all listed here, and we can drill into all of them as we go. So, this is pretty neat. It is important to realize that, when we run this, it's possible to get a lot of these generating. And that's the one I did. The one I just expanded there, I was clicking through things, was the one I did in the interface. I didn't put any limits on it, so there was a lot more of those child jobs. All right, let's look at the icy garlic job. That was the script one. So it's completed. Right, it's all here, and we can look at the models and the child jobs, for how this ran. So let's take a peek at that. On this list, we see the algorithm that really won. Right, it's the voting ensemble, and because it was the winner, and we had the explainability on there, we see that link, and also the accuracy that it won with. Right, so 0.953. For it. So let's jump over to the explanation to see, what this model actually kind of figured out. So when we look at the explanation for the model, there's a lot in here. I'm not going to explain a lot of it. It is the child job that we're actually looking at with the explanations, but we can see things like the feature importance, all of these things to explain this model. So you can drill into it, why this one's pretty good. So a lot of information. We're not going to go through every little bit of this, but it's pretty neat. The witty carpet job. Okay, let's go back to the parent. The icy garlic job. I love the names. And we look at the models and child jobs in here, right? We can actually see which algorithms are used for all of these, and if we had a lot more, we could go through all the pages and see what's what's going on with it, and so that isn't too bad. And we can see the accuracy and everything for all of them. Okay, we can also look at data guardrails, and so if you recall, looking at any of the automatic featureization that was enabled. This is where when it's automatic and it looks at things. So. To make sure that any of the normalization and scaling options are really applied to the data as much as AutoML will really support, right? So from here, we'll see that it evaluated whether or not we had any missing feature values that we needed to impute. In this one, there were nothing that was missing. It's all passed. All right, so our training data was pretty good for that. The class balancing detection, just above it, down the bottom, high cardinality feature detection. And again, all of these passed, no problem. And keep in mind, the one that we did in the script, it actually used slightly better data than the one that I demonstrated with doing it in the interface, right? I didn't clean up a lot of the stuff in the interface. Like the patient ID was actually in the interface version of the AutoML job that I submitted. Anyway, so this actually had pretty good clean data, which is pretty ideal for what we want, right? So that, ideally, we've already cleaned this up before it ever gets here, and we don't want AutoML kind of guessing. It does a pretty good job of it, but as a data scientist, I really want to have much better control over it. So, all right. Let's see, what else? Models and child jobs, we talked about in here, so lots of things that we can drill into. The accuracy, you can, as a reminder, you can play with what metric you're using to rank these, right? That's totally up to you. And I think we're pretty good. All right, let's go back over to the content and wrap up this video. So one of the challenges of training several models is being able to group related models together so we can compare their training results. That way we can separate models that are focused on solving one business problem away from a different set of models that are being developed for a different business problem. The way that we group models together is by using experiments. And a simple way of thinking about experiments is you can think of it as a label that's applied to a model so that when we view an experiment, we can see all of the models that have been labeled with the same value, aka the experiment. So to make this a little more complicated, it's possible to do model training outside of the Azure Machine Learning workspace. So imagine for a second that a data scientist trained a model on their laptop. How would we know that it even exists? And to take that a step further, if we did know it existed, how would it align with the other models that we've trained within the Azure Machine Learning Service, for example? The way that we would manage that is by using the ML Flow library. The ML Flow library is an open source library that is designed for tracking and managing machine learning experiments, and it allows us to log our model training to the Azure Machine Learning workspace by using the ML Flow tracking component. By doing that, not only do we get visibility about the model being trained, even if it's been trained outside of the machine learning workspace, but we can also track the details of the experiment, such as the parameters, metrics, and artifacts of the experiment. Since this video is focused on using AutoML, it's worth noting that many of the algorithms that AutoML uses supports auto-logging, which means that all of the details of that model run, such as the parameters and the metrics that are used, will be automatically logged for you. If you want to use ML Flow, you will need to ensure that the libraries are installed in the environment that you're using for training. If we're talking about compute inside of the Azure Machine Learning workspace, such as compute instances, clusters, or the serverless options, ML Flow is already installed. If you're doing model training on compute that is outside of that, such as on your own device, like a laptop, then you'll need to install the ML Flow package, as well as the Azure ML-ML Flow package into your environment. After the ML Flow packages are installed, the next thing that we need to do is set the tracking URI to your Azure Machine Learning service. You can find this tracking URI on the overview page of your service in the Azure portal interface. The next thing that we need to do is to set the experiment name so that the information that ML Flow provides for machine learning workspace will be properly categorized with an experiment. That way, if we have other models that are being trained from other environments, or if we have several runs of the same experiment, we can then compare the results together under one experiment. In order to do this in the Python SDK, as you can see on the slide here, we simply use the setExperiment function and set the experiment name to the name of the experiment that we want to use. We'll be discussing using ML Flow more in a later video. And that brings us to the end of this video about using automated machine learning to create experiments and to test many algorithms and settings at the same time. We also managed to sneak in a little bit of an introduction to ML Flow and how it can be used to help with the tracking for our experiments, even if they're being executed outside of the Azure Machine Learning Service. I hope that you've enjoyed this video, and I hope that we see you again as you continue on through this training series on the Azure Machine Learning Service. Thanks for watching. Hi there. My name is Neil McIsaac, and I'm a Microsoft technical trainer. In this video, we'll be focusing on optimizing our model training. We'll start by looking at how we would run a training script as a command job. We'll then cover how to track model training with ML Flow and jobs. And if you've seen a previous video where we introduced ML Flow, we'll go into a little more depth here. And then, and I think this is the big takeaway in this video, We'll cover how to perform hyperparameter tuning within the service. To wrap things up, we'll also show how to run pipelines within the Azure Machine Learning. So let's get started. At some point, after we complete enough experimentation, which is typically done using notebooks and compute instances, we need to start thinking about moving our code over into a production scenario where we'll build our models using larger amounts of data as well as need larger compute to process it. But most importantly, our code needs to be scalable, repeatable, and ready for automation. So although notebooks are ideal for experimentation and development, scripts are better for production workloads. In Azure Machine Learning, you can run a script as a command job. And when you submit a command job to run, you can configure parameters like the input data and the compute environment. The Azure Machine Learning Service also helps you track your work when running command jobs, so we can compare runs or investigate problems later on. If we used a notebook to do our experimentation and development, which is very typical, we'll need to convert the notebook over to a script before running it as a job. Some people actually use scripts right from the beginning to do their experimentation development, but most people would find working with scripts difficult, and so they use notebooks because it's easier to work with during the development stage. So if that's the case, we'll need to do the conversion between the notebook and the script. We'll need to do a couple of things, though, before we can run that code simply as a script. One of the first things you'll want to do is to remove any non-essential code, since ideally, scripts are streamlined to do the work and not really intended to be interactive like the way we would use a notebook. So things like showing graphs can be easily removed from those. The next thing we probably want to do is refactor the code into functions. I think an easy way of describing this is simply to make the code more readable, and functions can be an easy way to do this. Of course, before we do anything in a production environment, we test, 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 test. Now in this case, it's probably easiest to test your script within a compute instance by simply running it inside the terminal session. Hopefully after all of this, we have a production level script that's ready to go. Once we have our script ready, we can then run it as a job. So jobs in the Azure Machine Learning Service come in 3 different flavors. We have a command job, which is used to execute a single script, and it's probably the most typical type of job that we use. We also have what's called a sweep job that is designed to do hyperparameter tuning, and we'll look at hyperparameter tuning later on in this video. And lastly, we have a pipeline job, which is designed to run multiple scripts or components and is usually ideal for doing a series of steps and coordinating the logic flow between all of them. So when we go and configure a command job, we need to set a number of things in order for run. First, we need to set the code parameter. Now this is actually the path to the folder where the code lives, while the command property is used to specify the file to actually execute. So between these 2 parameters, you should have a complete path to the script that we want to execute. We also need to specify the environment, which will specify any of the packages and libraries that our script might need to have to make sure that they're available in order to make sure that everything executes properly. Next, we need to specify the compute that'll be used to actually run the script. We also need to set the display name for the job so we can identify it in the interface layer. And we also need to set the experiment name so we can group those related jobs together under the same experiment. Ideally, we want our scripts to be as reusable as possible. A great way to do this is by making sure that our script can accept parameters so that we can change settings during different executions. Since our script is based in Python, we need to import the argparse library into the script and then use the argument parser method to define the arguments for parameters. We also need to specify each of the parameters in the script, including setting the name, type, and default value. Those steps are done within the script itself. The next thing we need to do is to make sure that when we call the script, we set the parameters by name and set the values to what we want to use to run our script. In the example in this slide, you can see that we're calling the Python train.py script. And we're setting the parameters training data to the diabetes.csv file and the regularization rate, which is just here as reg rate, to a value of 0.01. So let's jump over to the workspace and see how to create a command job. All right, so let's start things off here with going over to a compute instance. And let's get into a terminal session. And on this one, so what I want to show you here is we have a notebook, right? And think very typically, I have a notebook, I've been doing experimentation. In this case, it's to do a classification model. I've been working with it a bunch. Let me, before I forget, let's switch this to the Azure ML kernel for this. So this is just a standard notebook, right? Where we're grabbing the data, we're splitting it up. We are going to train the model, do all these things. We can evaluate the model just below this, and figure out a bunch of the metrics for it. We're also plotting the ROC curve, right? So you see that it's going to show up on the screen. Now, the thing about this, and here's kind of the goal, is that we'd like to, while I'm talking here, I'm going to run all this. We'd like to take this and turn it into a script. So just to show that this does work, right? So you can see the data, it's splitting it up, doing all the stuff. And at the bottom of this, we go down, we'll see that not only does all the cells run, but also we're going to have the accuracy is in here, the AUC, we're going to have the plot at the end of it, right? So the thing is, if I were to take this and move it over to a script, I probably don't need this image, right? Maybe I want to save it or something like that. So the point is, I'm probably going to have to take this code and change it. So one of the first things is, this is a pretty good feature, is we can take this notebook and just simply export it as a PY file. And it's going to take all the code and just export it as whatever file name we want here. All right, so let's get a slightly better name. And if it exists, we can overwrite it. So that's going to be pretty good. Let's do the export. So let's create that. And as soon as we do that, as soon as that goes, let's go. Let's go over and look at what it actually created, right? So here's the export. It really is all of the sections that we had in code exported out. Now, at this point, though, remember that the goal here is to be able to take what we had in the notebook, which is designed to be much more interactive, and take this code and make it so that it can run on its own. So, high level, we probably want to go through and fix it up. We can run it, so we can save and run this, make sure it works okay. So pretend I cleaned it up. I just want to point out that it's still doing everything, right? It's reading the data, splitting the data, training the model. It's doing everything, but notice I don't see my plot. I don't see that part because it just doesn't go out to the terminal interface. So I could probably go back and remove that code. But the good news is that I can see that this works, right? And that's kind of one of the important parts. Now, I could take that further and say, well, let's make this script much nicer and all that, but we'll pretend we did that. So let's go over to a different PY file that we've sort of done all that already. So you can see on this one, we have things broken down into functions, right? Instead of just one simple PY script, we have a main function here, and the main function has all the function that's calling. So get data, we're going to split the data, we're going to train the model, we're going to evaluate that model. And then we have the definitions of all those functions, get data, right? So the first one, and right down here, split data, right? So we see all the functions in here and all the code that goes into it. So this is maybe a little more practical for a production level script. We also have arguments. Remember that ideally our script should be able to be parameterized, right? So I can pass parameters to it. In this case, it'll accept a training data argument. And the way to, so you'll see like path and variables kind of get used through this, but way down the bottom, all right, let's come down here. You'll see that it's basically, when we set up the script, and this is just kind of standard Python here, we're using the parse args function to parse all the arguments. This is standard Python. And then we're passing those arguments into like the main method and whatnot. So that parse args is set up here to have that training data and regularization rate as two parameters, and where there any defaults with them and whatnot. So the training data one doesn't have any defaults, right? Just the regularization rate. And so what happens if we don't supply that, right? As kind of a question. So we're gonna check that out here in just a second. So let's pretend we're still testing this. We're gonna save and run it. And what we get is a big error, right? If you look at this, so you get a trace back, being thrown from it. And why is that? Well, the command here, Python and then our py file, if you really look at this, it's invalid file path or buffer object. It's like, okay, if you really dive into this, it's because we didn't supply that parameter on it. So when we run this script, we need to run it and pass that argument to it. So let's do that, right? So I'm just gonna make sure we're in the right directory here. Actually, now that I'm looking at the directory we're in, since I'm already typing, I'll put it in anyway. We're kind of there already, so that's fine. We're in the right directory. So let's run this Python command. So it's going to be Python, and then our py file, if I can type it. If I can type it. So train model parameters py. And then at the end of this, we're going to supply the argument that we need. In this case, it's going to be the training data, which is going to be the diabetes.csv. And, oh, we got an error. Let's see. That should be okay. Oh, I think I see it. So it was just another typo. It was diabetes. Let's get that R out of there. And let's just run that. Oh, fix that up. There we go. If only I could type. So let's run that, and you'll see that it reads the data, splits it, does the training of the model, all of the things that we're kind of looking for, thumbs up. And now it's parameterized as well, so I could actually pass, different training data to it. All right. So that's pretty good to see that we now have a script. Okay, so what next, right? We have this production level script. Let's talk. Let's go over and look at command jobs, right? Because if we're doing training on a routine, scheduling, etc., we want to put everything in command jobs. So let me do just a little quick plumbing here first to make sure we're all signed in, and we get the ML client real quick. Okay, so I just jumped around there a little bit. So let's talk about command jobs. Command jobs, right? Earlier when we were talking about it, we just have a bunch of parameters that we want to set on it. So let's go down and look at that in the code. And you'll see that what we're creating is a command style job, and it's just the keyword command. The code parameter, that code argument, is the directory that we're talking about. And then the command argument is actually the py file that we need to point to. It's really the command, right? So Python space and then the py file. But it also has any parameters that we might want to pass. Now in Python, you might make this a lot more dynamic, so it's not hard-coded here, but this works. The rest of this, environment, right? We talked about those earlier in the course. So we can specify that. We can specify the compute that it's going to run in, so the rest of the bits of the job. And the big part of this is that, that script that we had that we just turned into a production level script, we can now use this in a production environment. So we're going to call the creator update command for jobs. And from that, we get the URL being returned back. So our job is now submitted and it's off and running doing the training. All right, so if we go look at it, right, oops, we'll see that the job is there. So diabetes train script, it is queued, right, doing the work. Now at this point, because the job is using the cluster, it is going to be spinning up that cluster to go and do everything, which is going to take a few minutes for the cluster to go. That's just because that's the compute that we selected on it, but it will actually go and complete the job as needed. So and it's going to do all the steps that we just saw, just in a much better environment, because we can do things like schedule these, right, which is going to be a little more critical, or call them on demand, and it's all configured for us. Okay. So with that, let's go back to some content. In a previous video in this course, we introduced ML Flow. Since we're discussing how to execute jobs here, which are going to be script-based, it makes sense that we would use ML Flow to track our model training. So let's take a closer look at that. Just as a reminder, ML Flow is an open source package that helps us to manage the machine learning lifecycle. If you want to use ML Flow in any of your code, you need to ensure that the ML Flow and the Azure ML-ML Flow packages are both installed into your compute environment. These packages are already installed on the compute that's provided by the Azure Machine Learning Service. So lastly, when we're using the ML Flow library, we can choose to enable auto-logging by using the mlflow.autolog function if our algorithm supports it. Or we can use the logging functions library to manually log data from our script. Let's take a closer look at how to configure logging with ML Flow. If our training library supports auto-logging, then it's just a matter of enabling the auto-log function, right? We just basically call it and we turn it on. All of the parameters, metrics, and artifacts would be automatically logged without us having to do anything else. So for example, libraries like TensorFlow and PyTorch, they all support auto-logging. So it's just a matter of turning it on, which is great. If our training libraries don't support auto-logging, or if we would like to log additional information for a training library that does support auto-logging, we can add calls to these ML Flow log methods to record the data. The first one, log param, can log a key value parameter, so we can see what parameters were set when we executed the job. The second one, log metric, can log a single key value metric, and in this case, the metric must be a number. This would typically be used to show metrics from a model like accuracy or area under the curve. The last one is log artifact. This one is used to log a file and is typically used to record things like plots as image files. So for example, if you wanted to record something like the area under the curve plot as an image, you can do that with this method. Once we run our script and record things like metrics and plots, we can see the results in the Azure Machine Learning Studio interface under the details of the experiment run, where we can see the log parameters under the Details tab. We can see the logged metrics under the Metrics tab, and we can find any of the logged artifacts under the Images tab. If we want to retrieve the experiment runs programmatically using the Python SDK, we can also do that. We can start by listing all of the experiments using the search experiments method in the ML Flow library. Once we retrieve the list of experiments, we can use a specific experiment ID to call the search runs method and retrieve all of the details of that specific run. All right, so let's take a moment and see how this works with the demo. All right, so let's talk about using ML Flow here. So I'm going to start off with this notebook, right? Using ML Flow to track jobs, and yeah, so basic notebook to start off with. Where I already ran the beginning where we get the ML client and everything, and we're going to grab our data. So for the script files, we're going to write out, And the very first thing that we're going to do, so after we do that part, writing out to the source directory, is we're going to write out this script file. Right? So this is just generating the file. And inside of this, because we're using MLflow, we have an import statement for it to start things off with. As we come down a little bit, this is just doing a kind of a typical training model. So we get the data, we split it, we train the model, evaluate the model, all that's still there. And all of these are within functions, of course, right? So right here, when we train the model, right below this, we have mlflow.logParam, where we're going to log the parameter for this, right? The hyperparameter. So the regularization rate, right? And the value for it. And of course, we're using a logistic regression model for this. So that's going to return the model. And then when we evaluate the model, we can log the metric that we collected from it. So this first one, we have the accuracy, and then just below this, mlflow.logMetric, the AUC, the area under the curve. And the last thing we're going to do when we evaluate, we're going to plot the ROC curve. And since we're talking about MLflow, just down the bottom, it's log artifact. And then we're going to log the artifact, the ping file, the PNG file. And what this should do is, show up in the interface, and we'll show that in a little bit. So the rest of this is just, doing the parse args and everything that we saw in some previous commands. So let's write this out. We'll create that py file. And let's go down, that's all written out. And let's queue up a job to do all this. So again, we're just making it go. The big difference on this one is that this is actually marked up with MLflow. So let's run it. And of course, we have a job that we can monitor now. This is going to take a little bit, so let's jump over to it. And once this loads, you'll see that the job is queued, right, currently. So it's going to take a little bit because remember, command jobs, this is set to the cluster needs to start up, it needs to do the work, all of those things need to happen. So we'll wait for a little bit. Well, let's refresh, see if it's started to run yet. Not yet. There we go, so now it's running. All right, see there, right there, that's running. And we could try being patient and keep clicking the refresh button. Usually at this point, we'd probably go get a coffee or something. Go get a beverage. Right, because it does take a little bit, even though it's a pretty small job for this. Since this video has been pre-recorded, we've sped up this section to save you a bit of time waiting for this to complete. Go. All right, we just saw the notification come in that it's completed now. So if you see a refresh, it's now completed. And now we can go look at the outputs, right? So let's go over to output and logs. And on this one, we see that in the standard log text, we see the output, so it did all of its work. But what we're a little more interested in are the MLflow artifacts. So we can see the ROC curve PNG, that was one just from the output. But if we go over to images, right, because we logged it, logged the artifact, we actually see it here now. Right? So anything that's there for artifacts there, for metrics, we see the metrics that we logged. So the accuracy and the AUC, the area under the curve, are both logged in here, so whatever metrics we want. And on the overview page, we see the regularization rate way over here under params, right? So that one is when we did the log param right at the beginning of it. All right, so as you can see, we can log all kinds of things with MLflow. All right, so let's jump back over to the content here, and we'll talk about hyperparameter tuning, which is awesome. So one of the biggest challenges that a data scientist has with respect to training a model is deciding on which algorithm to use, and also the hyperparameter values to use. We need to figure that out so we can try and produce the best model. A hyperparameter represents individual settings that we would set on a training algorithm. So, for example, maybe the regularization rate to set on a logistic regression algorithm. The reason these are not referred to as parameters is because within the machine learning space, parameters actually refer to the values determined from the training features. So to avoid any confusion, we use the name hyperparameter to refer to the values that we would set on a training algorithm to execute. When we're talking about hyperparameter tuning, we're configuring the values that we want to set a specific hyperparameter to, including using different values to create different models, so that we can compare the impact of different hyperparameter values on the model training. In the Azure Machine Learning workspace, we would use a sweep job to tune the hyperparameters. We would start by including an argument for each hyperparameter that we want to vary within the training script. We would then configure and run the sweep job with each hyperparameter configured with the different values for that hyperparameter that we want to use to generate multiple models with our job. After we do that, we would run our sweep job and simply view the results. So let's take a closer look at how to define the values that we want to use to tune our hyperparameters. First, we need to decide on whether we want to use discrete or continuous hyperparameters. Discrete hyperparameters are used when we set the hyperparameter to a finite set of values like 1, 2, 3, and 4. And continuous hyperparameters are used when the value could come from an infinite set of possibilities. For example, when we select a value from a range like any decimal value between 0 and 1. The settings that we use to define the set of values to use is referred to as a search space. When we configure our hyperparameter tuning, we need to select the type of sampling method that we want to use. The Azure Machine Learning Service supports grid sampling, random sampling, and Bayesian sampling. Grid sampling can only be used on discrete hyperparameters and will try every possible combination of the values that we specify. So for example, if we configure a hyperparameter to use 5 specific values using grid sampling, we would produce 5 different models, one for each of the values. If we had 2 hyperparameters and each of them were set to 5 values, and again using grid sampling, we would end up producing 25 models from the sweep job because we need to go through every combination of those 2 hyperparameters and build models from that. So each parameter, each combination we need to do. Random sampling behaves just as the name implies, in that it will randomly select a value for the hyperparameter, and this can be used with either discrete or continuous sampling. The last method, Bayesian, is a sampling method that will choose hyperparameter values based on the Bayesian optimization algorithm. The idea is that it selects values that will result in improved performance based on the previous selections. This one can only be used with the choice, uniform, and Q-uniform parameter expressions, and it's not possible to use it with an early termination policy, which we're going to look at next. Early termination policies are used to limit the number of trials that our sweep job would run. The idea here is that as we're running a lot of jobs, if we determine that a model is not producing better results than the previous trained models, we can stop wasting time training the model by stopping it early. This can save us valuable compute, which will translate into savings. We do have to consider our search space and which sampling method our sweep job is configured with, because early terminations are not supported for all of them. That being said, if we have a large number of hyperparameter values, especially when we're using continuous hyperparameters, we could be set up to create a very large number of models during a sweep job. So in that case, configuring an early termination policy would be an ideal way to limit the number of executions that we would have. When we configure an early termination policy, we need to specify which policy type we're using, as well as the settings for that policy. All of the early termination policies have two main parameters that we need to set. The first parameter is to configure the evaluation interval, which specifies how often we'll evaluate the policy. So for example, an evaluation interval set to 1 means that we'll evaluate this policy on every single trial. The other parameter is the delay evaluation parameter. This parameter specifies a number of trials to wait before we start evaluating the policy. This parameter is useful since we probably don't want to evaluate our policy when we only have a few trials that have been executed. We just don't have enough information at that point to compare the newer trials to. The three policy types that are supported are bandit policies, median stopping policies, and truncation selection policies. Let's take a look at an example of each one of those. The first example is a bandit policy. Bandit policies will stop a trial if the performance is too far away from the leading trial performance. Now, when I think of this policy, I think of the old Western movies where there's a bandit that just robbed the bank, for example, trying to get away on their horse with the sheriff and the posse trying to chase them down. If the people chasing them get too far away, they might as well go home, right? Because they're never going to catch the bandit. Only the people that keep up with the bandit should keep riding. So in the example in the slide, we see that we're configuring a bandit policy and specifying a slack amount of 0.2. The delay evaluation of 5 and an evaluation interval of 1. What this means is that any trial that falls out of the 0.2 margin that's specified in the slack amount will be terminated. Because the delay evaluation is set to 5, we won't start calculating this policy until after the 5th trial. After that, the policy will be evaluated for each trial since the evaluation interval is set to 1, so each time. And as you can see from the two plots, on the left-hand side, the 6th trial was within 0.2 of the accuracy of the best trial, and so it was kept. But on the right-hand side, the 6th trial fell below this margin and was terminated early. Keep in mind that it's possible for a later trial to become the new bandit. In other words, a later trial could become the new leader, which will affect where the margin is moving forward. The next policy that we're looking at is the median stopping policy. This is similar to the bandit policy, but the calculation of where we draw the line is a little bit different. In this case, we calculate the median of the performance metric, and any of the trials below this median line will be terminated early. In this example, we see that we only need to specify the delay evaluation and the evaluation interval parameters. The other thing is that this policy is more likely to change since the median value will change as more trials go above that line. The last policy is the truncation selection policy. This policy specifies a truncation percentage. And what that means is if a trial's performance metric is within the bottom X percent, in this example, 20%, it's terminated early. You can see within the plot of the trial performance on the left side that the performance of the 5th trial is not in the bottom 20%, and so it's kept. On the plot on the right-hand side, since the 5th trial is in the bottom 20%, it's terminated early. So setting early termination policies can be a great way to optimize the compute that we'd use to execute your sweep job. Now, let's take a look at a demo on how to do hyperparameter tuning. All right, let's start things off with looking at the training script that we're going to sort of base everything off. So this is still just a typical training script where we set up the source. So we've seen this style before, where we want to play with the script files. We're going to write out our training py file, our training script. And there's really nothing different here. So I'm going to just do this. It's going to read the data, split the data, all of these things that we did before in here. So training the model. There's nothing really that special. With this one, you see that the regularization rate, so the reg rate, is here under args, just to note that it's an argument. And we do have things like the ML flow statements and all that in it. But our focus here is really about doing hyperparameterization. So the first part is really say, hey, we have a command job where we want to go run that script. And so being able to configure the hyperparameter, right, that we exposed as an argument is really just setting up the command job for this. So the code and the command is kind of the same thing, but you see the regularization rate right here as an argument. So making sure that our script supports it, and then we can pass a value to it, right? So for those inputs, we can set a value for it. Now, the catch with this, let's run it because that's going to spawn a little bit of work. The catch with this as a data scientist, we put one value in here, we run it, we see the results, we go change this rate, we run it again with a different rate and look at those results. We run it again with another rate. How many times do we have to do this and to see all these different values? So this is really, I think, kind of establishing the point is we have a hyperparameter, but we're not really taking advantage of being able to tune it that effectively. So let's go down, right? So yeah, that's we do have a job that spawned to that, of course, but let's go down and talk a little bit more about actually doing the tuning part. So the first thing we want to do is set up what we refer to as the search space. And this is when we set up the parameter, the hyperparameter, to be set to a number of values. So in this case, we're using the choice function to say one of these three discrete values. So the choice function will give us discrete values. So 0.01, 0.1, and 1, three different regularization rates that we want to run everything for. And we are going to set up a sweep job, right? So we're going to see that in just a second. So, so let's get that all set up. All right, let's run it. And let's come down and configure this sweep job. So one of the things about this is that, we have the parameter that we just set up, the hyperparameter that we just set up. When we go to pass it here, we want to specify what type of sampling we're going to do. In this case, it's going to be grid. And if you remember, grid says we're going to take every combination of values. So in this case, we only have one hyperparameter with three values. So we are going to get three models from this. We can set limits on this for how many trials we're running through, of course. But I think the big point here is that is what that hyperparameter is really set to. So let's run that. That's going to configure our sweep job. All right, so that should be all good. Let's submit it. All right, so that's going to be the creator update for the sweep job. So now we can, we have the link to monitor it. So let's go over and yeah, I think we're pretty good to go over and look at monitoring here with that. All right, so it does take a minute to go. So, all right, let's go over here. It's not remember the jobs are not the fastest thing. So we see that they're running now, which is good. Now, depending on how many parameters we're actually supplying to this, we could potentially have a lot of trials, a lot of things going on for this. And so with this one, if we scroll down on the trials page, we can actually see the different trials running, but look at the regularization rate. Notice how it's running through the values. Now we only see 2 here because we set a limit of the number of parallel trials was going to be limited to 2. That was when we set up the sweep job, right? So these are both there. And once one of those finishes, it would actually go and spawn the 3rd job and kind of keep going through it. Now do keep in mind, if we had a lot of these, like different parameters, we would see a lot more jobs, child jobs getting spawned for that. All right. So that's pretty neat. That's basically hyperparameter tuning. There's a lot more to configure the parameters, but let's go back to our content so we can get going into components and pipelines next. In the Azure Machine Learning Service, a pipeline is a series of machine learning tasks in which each task is implemented as a step. Basically, this is a form of a workflow. We can use pipelines to coordinate machine learning tasks like model training and testing. Components are a foundational part of creating pipelines. since these essentially represent tasks that need to be completed. And we'll use a series of components in a pipeline to create a job. Components are reusable scripts that are packaged as a component. The challenge here is deciding on how to break down a larger process into smaller pieces so that we can much better reuse those pieces into other processes. Some examples of components might be a component that trains a model, or one that prepares data in a specific way for your organization, or maybe it evaluates a model that's been trained. The advantage here is that since it's basically just a Python script, the component can do a task that is specific to your organization. In other words, if there is a specific way that data needs to be prepared in your organization, you can create a reusable component that other data scientists can use, which can help to ensure that the data is processed very consistently across your organization. As I mentioned, a component is basically a script, but we need it to play nicely with others within the machine learning service. So we need to take our script and add metadata that will describe the component to the machine learning service so that others will know what it is, and we need to define the interface for the script. Remember that the component will be part of a pipeline, which means we'll have many components doing the work, and one component will need to pass data to another component. The interfaces that you define on your component will define what data can be passed in or out of your component. This will also help restrict what components we can connect to. In other words, if we connect two components, the output of one component needs to match the input of the other component. In order to create a component, we need to have the script that does the actual work, as well as a YAML file that will define the component metadata, interface, and configuration of that script. Once we build the component, we'll need to register it in the machine learning service. We can use the Studio interface, or we can register the component using the Python SDK by using the create or update method on the components class, which is what you see an example of on the slide here. Once the component is registered, we can start using it within a pipeline. So let's talk about pipelines. Pipelines are really a form of workflow, but let's take a step back for a second and look at the bigger picture. Could we do all of the steps that we need to in a script that runs as a command job? Sure. Could we separate our command job into multiple scripts and have something like a master script call all the child scripts to do the workflow? Absolutely. So why would I want to go through all the trouble of packaging my scripts up as components? Well, if you leave everything as just scripts, what about things like version control? Or do I just update the script right in its place? Or if I was going to call a script, how would I discover what parameters to pass to it? What if I had a script that called a bunch of child scripts? How easily would it be for me to understand what's going on in it, especially if I wasn't the author that made it all? The point is that by packaging our scripts into components, we get a much better reusable package for our script. And then we can use it in a pipeline. We can see it more graphically, which helps others to understand it. If we focus entirely on using just scripts, they can actually get pretty messy fast. Also, components support versions, so we can track changes much better with them. We can define our pipeline programmatically using a YAML definition, or we can do it in the Python SDK using the pipeline function to create the YAML file for us. We can also create pipelines visually in the Azure Machine Learning Studio. Of course, once we build a pipeline, we can then run it as a job. So pipeline jobs are really just jobs that simply run a pipeline. Of course, we can schedule them to run on an interval. If we want to schedule them using the Python SDK, we can do that. We would simply use the job schedule class to assign a schedule to the job. And if you wanted that job schedule to repeat, we would use the recurring trigger class with the job schedule class to create a recurring schedule using the Python SDK. So let's jump into a demo and see how we can use components and pipelines. All right, let's start things off with we're going to use a notebook for this, but start things off with building our components and pipelines. We're going to use a notebook to do all of this. So all the plumbing that we've seen before, we're going to get that the source folder created. And the reason is because we're going to make a couple of scripts here. So the prep data py file that I just highlighted, this is a pretty standard, prepping of the data. So getting the data, cleaning it up, doing any normalization, and then putting it out as a CSV. You notice that we're not training or evaluating a model for this. So this script is all about prepping the data. And it will accept an input data and output data parameter arguments. So both of these here, they're both of type string. But this is going to say, like, here's the data that we need you to prep, and this is where we want you to output it to. So this is all there. Let's write this out and get that py file. And once we do that, we can come down to the next py file that we want to do, the next script file, and this is going to do the model training itself. So in the main in this, we're going to get the data, right? Again, notice it's set as an argument. We're going to split it. We're going to do the training. And further down, same idea. We have the functions to do this, like to train the model, to evaluate the model. But you will notice that we do have arguments for this, right? So look at our parse args. We have the training data that needs to come into it. We have the regularization rate and also the model output, where to put the model that we're going to produce. Where should that go? So another script that's parameterized. And those are both, I think, pretty simple. So let's get that built. And now let's start looking at the magic. So this is where we're going to take those scripts and we're going to wrap it into a component, right? So what we need to do for that is really define the metadata. So if we take the prep data, that script, we're going to create a YAML file to really reflect that. So we're going to give it the name. This is just prep data to match the name. We'll give it a version. We'll specify all the inputs and outputs, right? So you see the input data. You see that it's of type URI. Output data is a folder. So right there is the URI. Right here is the folder for the output. So this is defining those parameters. Now this is the YAML to define the component. The environment, and of course we need to specify what script we're pointing it to. So that's the prep data script. And then how the input and output match the arguments for it. So it's just a definition. This is simply going to write out the YAML file. So I ran that and that's all produced. We're going to do almost the same thing with the train model. The py file, we're going to make a YAML file for it. And again, it's going to have its inputs defined, potentially with defaults, its outputs defined here, and then the actual Python command to say, and this is what we're going to run for this component. So components are really just a wrapper around these scripts. And when we have these wrappers, what it allows us to do is to go over to the Azure Machine Learning workspace here, and we can load them into the environment, right? So say, here's the YAML file with the definition, like make this component basically available to other things in the Azure Machine Learning workspace. And that's all it really takes to do that. Now, once we have that, we can go further down into building a pipeline. And if you recall, whoops, my bad. Habit of double clicking those. But if you recall, pipelines are really just a series of components that we're going to run together. So it can shorten this script quite a bit. But more importantly, because we made those components, this can be a little easier to reuse those. So this one, we're making a diabetes classification pipeline where we call the prep data. And right below that, the train decision tree, right? And these are really the references out to those two components that we were just talking about. And we're going to wrap these up into a pipeline. So we have a decorator here to say this is a pipeline definition for this. And so let's run that. That's just really going to kind of create the definition for it. And then let's see. Yeah, so, I do want to mention that, the prep data here. So this prep data is going to return clean data. I knew I was forgetting something. So the clean data, if you look at the input for the trained decision tree, it's that clean data is being passed to it as one of the parameters into that trained decision tree right there. So this is one of the ways that we can have components to say the output of one component can be the input of another component. All right, so that's all run. And it's going to be, we're going to return, the outputs from these so we can see them later on, and define that job, right? So yeah, I ran that. All right, let's come down a little bit. Let's look at running, just showing the pipeline job, the definition for it. We can see all of the metadata around the pipeline job definition, right? So it's really, from here it's type pipeline job. It's saying, the inputs for it, then the outputs for it. So it's really, this is really simply the definition for it. And the jobs inside of it, the clean data job, the definition for it. So think all the components that are really in it to go and run. And all these components can have a lot of their own settings for everything as well. So that's pretty good. Now, to play around with this a little bit, what this is going to do is we're going to change a few things. I'm just going to highlight this one, default compute and default data store. So, and notice their settings, AML cluster and workspace blob store. So let's run that. What this is doing is changing the definition for this. So if we start looking through this, we should see these different settings, right, for how this pipeline job is going to run. So it's still just simply a job definition. There's just typically a lot more going on because of all the components. So on this one, let's see if we can find one of them. I know a couple of them are at the very bottom, so see if we can spot them. All right, yeah, we'll just use the ones at the bottom here. So the two at the bottom, default data store and default compute, that's the settings that we set. And so workspace, blob store, and AML cluster. So you notice that, yes, we can do it. All right, it's still a job. We still need to submit it. It still needs to go against compute and do all the running. So let's get that going to do everything. And of course, those components are actually like child jobs within it. So here we go with the run. And this will take a little bit to actually go and do. So you've seen that jobs can take a little while to go. I think the big thing here is that we're able to take those scripts and wrap them as components. And then the job, we're not going to stick around to watch that job go at this one. It takes a little bit of time to do that. So hopefully that makes sense why we might want to take those scripts and turn them into components and start using pipelines for it, because there is a certain amount of reusability when we do that. Okay, let's jump back to the content where we're going to just do a quick recap about everything that we've seen in this video. So let's move over there. And that brings us to the end. I hope that this video helped with your understanding of how to build and use scripts to support jobs, as well as how to use ML Flow to track those jobs. Hyperparameter tuning and how to configure a sweep job was also a big part of what we covered in this video. And in the last part, we spent some time on how to build components and pipelines. I hope that we see you again as you continue through this training series. Thank you for watching. Hi there. My name is Neil McIsaac, and I'm a Microsoft Technical Trainer. In this video, we'll be covering how to manage and evaluate models using the Azure Machine Learning Service. Specifically, we'll look at how to register an ML Flow model in Azure Machine Learning, and we'll also spend some time reviewing Responsible AI and the Responsible AI dashboard. So, let's get started. If you recall earlier in this course, we can spend a lot of time developing models, and these models, and I mean the actual files for them, they can be spread all over the place. We also looked at ML Flow and how it can help us log information about these models so that we can keep better track of them no matter where they're developed. At some point though, we need to get those models over to production. More specifically, is that we need to have them deployed out into a real-time or batch endpoint. But how do we control the process of organizing which models are ready for deployment, especially if they're potentially spread all over the place? The way that we do this is by registering the model with the Azure Machine Learning Service. When we register the model with the service, we end up creating an ML model file, which is going to contain the model's metadata and allows us to use the model directly in things like pipelines or deployments. You can see in the slide here that an ML model file has been created, which we can see in the outputs and logs page. In this example, the model was logged using MLflow's auto log feature. It's possible to log the model manually as well, but in order to do that, we have to define the signature of the model. The signature is the definition of the inputs and outputs that the model will accept. In other words, what data needs to be passed to it to generate a prediction as input, and then what data would be returned from the model as the prediction. The ML model file format consists of metadata that describes our model. The file usually includes the artifact path, which is the location of where the model is logged to, the flavor, which describes which machine learning library was used to create the model, the model UUID, which is simply the unique identifier for the registered model, the run ID, which is the identifier of the job run that created the model, and lastly, the signature, which describes the inputs and outputs of the model. Again, the inputs being the schema of the data that needs to be passed into the model when we want to generate a prediction, and the outputs being the predictions that are being returned. Once we have an ML model file generated, the last step is to register the model with the Azure Machine Learning Workspace. And you can do this using the Studio, the Azure CLI, or Python SDK. What this will do is add it to the model registry, where it can be more easily found within the Azure Machine Learning Workspace, as well as allow it to be used directly from the registry. For example, it's very easy to deploy the model to an endpoint from the registry. Now, let's do a quick demo on how to log and register a model using MLflow. All right, so let's start things off with looking at a notebook here. Whoops, I keep doing that. Where we're going to do auto logging with MLflow. So the first part of this, just setting up some of our data again, where we're going to put the script folders, the script files in the folder. And we'll start things off with this train model autolog py file, right? Now, the big difference here is we're going to simply just tell MLflow to autolog. And it's because we're using a logistic regression, and so we have an algorithm that supports this. We just turn it on. We don't really have to do anything else. We can if we want to, so we can specify things like log param and things like that. But because we're using autolog, this algorithm would automatically log everything for us. So this very first script that we create is just a standard training script that's going to do that. So let's submit this as a job. Again, I'm doing this quick because we've already looked at jobs for that. So this is the autolog py file. And let's get that running. There we go. So that looks pretty good. And of course, we have a link to our job if we want to look at it. But that's pretty good. Okay. So, there's a lot going on with autologging, and kind of what we looked at the last one, even though you turn on autologging, you can still specify some extra information about logging with MLflow. So in this one, we're going to specify the flavor with autologging. And similar idea is we have a script. It's still logistic regression. There's not too much here, but this one, notice there's a slight difference in this statement. We're using the scikit-learn, right, and then specifying autolog. So this is simply going to kind of force MLflow to say, oh, autolog, using this flavor. Everything else is actually the same in here, right? So any of the other log statements, right, so log param is in here. Any of these are really kind of the same, and there's not that big of a difference on the script. The big one is just when we do the autolog is we're specifying the flavor as part of that. So let's create that script, and let's come down and get this going as a command job. So this is the scikit-learn, and off it runs. So I have two jobs that have been submitted, and that looks pretty good. Okay, so another big part of doing the logging, and when we end up logging the model, which is kind of our target, is we need to think about the signature. So this next example is going to look at how to infer the signature. And this is really when we have data that has a schema and everything, can we do that? So with this one, notice the ML flow is autolog, but we're saying log model is false. A little further down, infer signature. So we're going to say, hey, here is the signature that we want to use. There's the input, there's the prediction data. So the X-train is the input, right? That's our training data. And the idea here is that, with the training data, we have the schema with it. And so we can say, well, this was what the data coming in should look like. On the backside, what should the model give us in return, right? So this is what is going to be the returned results, aka the predictions. And so again, we're just supplying the 2 bits of information here to say, here's the input, here's the output, and we have the schema for both, so let's go and define that signature. Last part is we're going to specify we want to log the model using this signature specifically. And again, we're doing it under this scikit-learn and everything. So the big difference in here is that we're not doing auto-logging for the model. We've set it up with a signature. So let's get this pipe file created and submitted as well. All right, so we get a number of jobs. So this is just the train model infer pipe file running. And it looks pretty good. Now, we can take this a step further where we supply the definition of the signature. The big difference on this one is you're going to see our signature is going to be based on a schema that we actually spend some time to define. Now, this can give you very granular control over what that signature looks like, right? So what types of data is coming in, the names of all these columns, all of that stuff, when we turn around deployment, it's going to be there. So we have that. We have an output schema as well, saying this is going to return a Boolean value, and we are going to create a model signature using the input, using the output. So we get a signature object. Now we have something that we can pass to the log model statement again. So where the infer signature does that for us, this one we're doing more manually. We're still ultimately getting a signature for it. So this just gave us more control. So let's run this one. So now we have our py file. We're getting some of the other command jobs coming in, completing, running and completing and whatnot. So some notifications there. All right, let's come down here and let's submit this as a job. So that's our model signature. We'll go and run that. And off it goes. Now, a big part of this, right, when we go and do all of our training and we want that model to get logged, we want to register the model so it shows up in the model's interface, right there in Azure Machine Learning. So all this is really going to do is say, hey, let's build a model. We're going to look at a return job. Let's grab from that job, right, the artifact for our model, right? So you see the path here all the way down to artifacts, paths model. We give it a name. The asset type is an ML flow model, right? So we do have a file for that. Get more stuff completed. And we are going to create or update that model to the models collection, basically, in here and have that show up. So we do need to have one that's run, and we did see some things that were completed. And that's why it's important that we're paying attention to that. So you see what job, right? This was the job that we were referring to, and the model from that is going to get deployed with that name. All right, so that isn't too bad. Let's go over to our jobs, and I do want to show actually just double check something here. Yeah, so this is I just wanted the name for that. So autolog.py. So this is the one that's completed, right? So that's the one that we submitted first. The other one, there's a bunch that are probably still running. So let's go look at this job specifically, right? And we're hoping, we saw a lot of notifications come in that things were completing. So let's use this very first one that is completed. And if we look at the outputs and logs for this, right, we see that it did everything. It read the data, did the split, all of these pieces. And so we can look at all the output for it, but what we are most interested in is the model. And so we have a model folder here, and we see the ML model file. So let's take a look at that. The ML model file is really all the metadata that we want to have describing our file. So in this case, what the flavor is, right? We see scikit-learn. We can see things like the pickle file, so right there. So in this case, the model was outputted as a pickle file. We have the signature for everything, right? And inputs and outputs for it. All of that is right there. So this is the auto log to go and generate that. Now, that becomes very useful because that ML model file makes it very easy to do things like registrations, and then once we register it, we can turn around and use it for deployments and everything much more easily. So let's come down to models, right? And we'll look to see, this is the one that we, I believe this is the one that we registered. And so we registered that model, this is on the list. So even though we have a bunch of models sitting in the file system, only one of them is listed here. The one that we created. We can deploy these real-time deployments. We'll talk about that in the next video. But this is going to really help us to manage like the list of models that we really care about, not just all of the models that we might be playing with. So I think these are the ones that we're going to be more focused on to probably get to production. So all right, with that, I think we're pretty good to jump back into some content. Right, now that we've talked about those models right there. So let's get back in there and we'll talk about the next section for this. All right, let's go. It's easy to focus on the accuracy of a model and continually try and improve it. However, how do we know if our model is doing predictions in a safe, trustworthy, and ethical way? So in this part of the video, we'll be covering what responsible AI is, as well as how to use the responsible AI dashboard in the Azure Machine Learning Workspace to help assess that. We here at Microsoft are very big on responsible AI, and we take it very seriously. It should be very important to all of us that the models that we develop and use are done so in a safe, trustworthy, and ethical way. That's actually a pretty broad statement, since that can mean many, many things. So let's look at some of the areas that we need to consider. First, it's important that any AI-based system treats everyone fairly and avoids affecting similarly situated groups of people in different ways. So for example, when AI systems provide guidance on medical treatment, loan applications, or employment, they should be making the same recommendations to everyone who has similar symptoms or financial circumstances, or for example, professional certifications. What we don't want to see is an AI model make decisions based on factors that are potentially irrelevant or even worse, harmful, such as age, gender, or ethnicity. This can be a very challenging area to determine whether or not a model is fair, as well as if particular features are influencing the model poorly. It might be really easy to simply eliminate features that might be deemed questionable out of the training data completely. However, if historical data was used in our model training, then some of the features might be introducing a bias without us realizing it. For example, if we were to train a model to help process loan applications, it might be obvious that data such as age or ethnicity should not be part of the training. However, if our trained data, which is really historical data that was biased with those features that we removed, such as granting loans to people over a particular age, even if we remove the age feature from our training data, we might actually be introducing the bias without realizing it, since our training data has already been affected by that bias. So a lot of the times, it might be better to keep features that would be considered inappropriate in model training simply to determine if a bias exists. We also want to consider reliability and safety. When we're evaluating a model with respect to reliability and safety, our goal is to understand if our model can respond safely to unexpected conditions and resist any harmful manipulation. However, that can be a very difficult task depending on the nature of the model that we're developing. Our focus here will tend to be to examine how failures occur within our model. So, for example, what the failure distribution is, and if any cohorts, which are subsets of the data, if they have a higher error rate than the overall benchmark. So privacy and security is another aspect of the model that we need to be concerned about. Since we're building this model based on data, is it possible for somebody to extract secure data, including private data, from the model? For a complete AI-based solution, this could mean everything from how the original data was collected and stored, to how it's used during training and testing the model, to controlling where the model is stored and who has access to it, or to limiting the potential for data to be extracted directly from the model. Of course, we also would like our AI solution to be as inclusive as possible. The overall challenge with this is that if our training data was collected from older systems, the training data may not have any inclusive data that we want. So this can be an ongoing challenge to build inclusive models. Across all of this, we would like our models to be transparent, which means that we have the visibility to understand how the decisions were made from the model. And we do this by focusing on interpretability and explanations. In the Azure Machine Learning Service, we can examine explanations a number of ways, as well as examine things like what-if scenarios. Lastly, it's important to remain accountable for how an AI solution performs, and this can include things like ensuring that an AI model prediction is not the final authority on critical decisions that may affect people's lives, or that we proactively monitor and assess an AI's performance over time, especially as we update our solution. Since all model training is based on data, we need to start with our data sets to evaluate if there are any issues with it. We can do that by performing data analysis on the data before we use it for training. This can include exploring the statistics of our data, including the distribution of the data across different cohorts and feature groups. Determining whether there are any issues with fairness, error analysis, or causality as a result of the dataset's distribution, or deciding if there are any areas that we need to collect more data to mitigate error, such as collecting data for underrepresented feature groups. Or maybe introducing noise into our data to help protect the underlying data from being extracted from the model. When we're evaluating our model for errors, we can use the error tree or error heat map views in our Responsible AI dashboard, along with cohort filtering to see if there are any groups that have a higher error rate than others. Once we identify those areas, we can dive further into the data to try and understand why it's different. A big part of evaluating our model is to examine feature importance, which is part of creating an explanation for a model. Feature importance quantifies the relative importance of each feature in the test data set as a whole, and it can help us identify the importance that each feature has in how it influences that model. We can evaluate the feature importance at the aggregate level or at the individual level. The aggregate level allows us to see how important a feature is for the overall data set. The individual feature importance allows us to examine the importance of features for an individual prediction, which is useful if we want to dive into a particular prediction and understand the why behind it. So in the two examples on the slide, on the left-hand side, we can see the aggregate feature importance, and you can see that income is the biggest influence over the predictions for all of the test data. On the right-hand side, for an individual prediction, we can see that the loan amount had the biggest influence in producing the prediction. since we're also trying to evaluate the fairness of our model. We can also see that age is the third largest influencer for our aggregate feature, which might be showing that it's an unfair bias. But on the right-hand side, for the individual feature importance, it has a much, much smaller impact. Of course, it takes time to really understand our data and any biases that it might have. So in the Responsible AI dashboard, we can filter our data for cohorts, which are simply subsets of the data. And we can also compare one cohort against another. That way, we can evaluate our model to see if there's a difference between different cohorts and their performance or their error rates. So for example, we might see that one cohort is getting a more favorable prediction than another cohort. Once we discover that, then the next step will be trying to determine why there is a difference. Using the Azure Machine Learning Service, we can create a responsible AI dashboard to help us evaluate all of this. In order to create one, we need to create a pipeline that has the Responsible AI Insights dashboard constructor on it and include one of the tool components for RAI, right, Responsible AI. And then we need to make sure that we use the Gather RAI Insights dashboard to collect all those insights into one dashboard. So let's go over to the portal and look at how to create and use the Responsible AI dashboard. All right, so to get started with creating the Responsible AI dashboard, right? I've opened a notebook up here, and some of the other ones we're going to start with, creating our data assets. But this one's going to be a little bit different than a lot of the demonstrations that we've done before. So just double checking that we've connected to everything. I did just double check that previous to this, that we do have our data. So it's just the diabetes, CSV and everything. One little thing that I did do is did make sure that we wrote the data out as a table. So it's really important that when we're doing the RAI, the Responsible AI dashboard, that we're basing our data, so training data, test data, et cetera, on ML tables. So that code was just do that from those Parquet files that I just highlighted. So we're setting up the paths for everything where training and test data is. And then we're going to go and get the data, right? So looking at making sure we have that ML table, right, for our training data and our test data. So both of those are there. So again, just referencing data on that one. Okay, so here's where the magic really happens for the Responsible AI dashboard, or RAI, as you'll hear me refer to it quite a bit. So we're going to get the client to our Azure ML registry, right? So this is just our workspace, basically, with the registry name. This is where we can pick up like the model that's registered, because we need to have a registered model to really work with the Responsible AI dashboard. So let's get a connection to it. So running that looks pretty good. So that works. All right, so, and this is going to help give us access to all those RAI components that's listed there. All right, oops, I keep double clicking those. So registering the model, we have a model that we need to register. Again, we need to use a registered model, so that's all this is. We saw this in the previous video, previous demo in this video. So there we go. That looks good. And now we're going to focus on the pipeline itself. So the first little bit, we want to, and remember the pipeline's building the dashboard. So we want to go and grab the model that we care about to build the dashboard for. So that all this code is really doing is going and getting the actual model ID, right, for that with the the Azure ML protocol in front of it. So Azure ML colon. All right, here's where the magic happens. We're using the registry. We're looking at these components from the RAI dashboard. We're going to go get the insight constructor, and this is the first thing that we need to do with the dashboard is get that constructor, and then from that, or really kind of adding to it, is we're going to add error analysis. We're going to add the explanations on that, and we're going to do the components called insight gather. But we're going to use these to add data to the Insight constructor, which is our kind of our dashboard. So this is just really going and grabbing the components, right? Remember the pipelines and components we talked about earlier, grabbing those components from that, but it has to be from the registry. Okay, once we do that, we do want to make a pipeline job. So here we have a pipeline, and this is going to, we just have it marked in as a decision pipeline. We are going to go through and do the work, right? So we have the target column name, the training data, test data for this pipeline. The title for it, so the RAI, Responsible AI Dashboard for Diabetes. And we can supply, our model input and everything. So a lot of bits. And I know I'm going through this a little bit fast. There's just a lot of detail for it. So here's where we add the error analysis. This is referring to the component earlier, right? The error analysis component that we retrieved. We have the component for explanations. And combine everything together with our Insights dashboard. There's our error analysis, there's explanations, and we end up creating a job. So remember that pipeline jobs are basically a series of components that are configured. We add them, create them, and then run that job. So for this one, we're going to get that going, and we do want to supply the input for this, the input for the training data and the test data. So again, these are ML tables, and refer to the diabetic data that we it was further up in the notebook. And then I'm going to come down and actually do the job, right? So the job. So we have our pipeline job kind of defined. We're going to set a few things like the target column. So these are the parameters for it. And training and test data, we're going to, there's a little bit of like just downloading the dashboard, so we're just going to output it in a spot. That's kind of a little workaround. That's pretty common. So let's get it running that. And so there's a little bit of an error there. Let's see what it, you know what? I forgot to run that. So it's just the previous cell that defined the data. All right. So we ran that to define it. We want to run the pipeline. So we have it with all the parameters. So this is just a function to submit the pipeline, right? So the jobs, create or update that pipeline job. Short version of it, it's fancier code for it than what we've seen in some of our other demos, but that's all it's doing is submitting that job, that pipeline job. All right, so that's off and running. And so this does take some time to go, but because it is a pipeline job, it is possible to go over and look at the GUI, right? So the user interface version of, let me close all this. Right, so here's the graphical interface for these pipelines. Let's see if I can clean this up a bit. I guess that's as narrow as it'll go. And so here we have all of the components, and in the middle is that dashboard constructor. All right, so the stuff across the top was the inputs and things like the model. So there's constructor, there's the error analysis, there's the explanation jobs, and those will get added to the Insights dashboard. And then of course we're producing the dashboard at the very end. Now this is a pipeline job, so similar to the jobs, we got to spin up the compute, we have to wait for this to go. So this will take some time to do that. So let's see how it's running here in a little bit. And we'll just happily wait. All right, let's just take a closer look at what's going on. So we see the dashboard constructor. I see the little stripes running. That's going to be a little bit for that to run. Since this video has been pre-recorded, we've sped up this section to save you a bit of time waiting for this to complete. Let's see a refresh how it's doing. Still going. There we go. All right, so the dashboard constructor, it's completed. What we should see now are the other two uh, components to run after that. So the error analysis and the explanation, those two jobs to go and do those. All right, so those are running. And of course, we're gonna have to wait for those as well. All right, so the explanation is finished. All right, and the error analysis is now finished. All right, so let's move this down a little bit further. We still have to finish the dashboard. So let's grab this and just move it down. So you see the gathering the insights, and then finally the dashboard being created at the end. So we just have to wait for that to run. This part of the process can take some time. So let me hit my magic fast forward button to jump to the good stuff. All right, now we have everything done. So see that everything's completed. That looks pretty good. So the dashboard hopefully is produced from this. It really should be. Everything seemed to run successfully. So we can actually view the responsible AI dashboard right from here. So let's go look at it. And this little prompt, I'll talk about it here in a second. We have our responsible AI dashboard here, right? So we see things like, the cohort configuration at the top. Because we did error analysis, we have a whole section for that. And, this is connected to a compute resource. And it can be connected. We want it to be running because it'll give us a lot more functionality for this one, right? And we'll see that as we kind of play around with this a little bit. We won't go through everything in here, but it's really just to give you an idea of what this responsible AI is really about. So we can see things like the error heat map. So if we move around here a little bit, if we hover over any of these, we can actually see, the statistics around what's correct, what's incorrect. We can kind of drill into them if we want to. So that can be really useful to see if we have a subset of data that is, a cohort, and we can filter for those cohorts as well. But we can see if we have a subset of data that's being treated unfairly, for example, because the error rate maybe is a little higher than normal. The heat map, now you notice the heat map, when I come down here a little bit, that everything's grayed out. So the features, I can't select the rows or anything. I can see the overall error rate and everything, but I really can't do anything with any of these. And the reason for that is because that's part of the additional functionality to connect to compute. So we'll circle back to this in a little bit. The compute's running, but we do need to connect to it and get that extra functionality a little bit. So we'll come back to that heat map and see us playing around with it. Okay, let's see. What else to show? There's a lot in here. So looking at the model overview, we can see things like the metrics with the data set, any of the features, how that compares. So sample size, accuracy scores, false positive and negative. So just basically our performance of like the model in this case. We can play around with what we're looking at, right? So the different metrics to see that. We can see things like, the probability distribution, metrics, to see the visualizations for it. You can see a confusion matrix if you want to. And we can play around with the labels. There's a lot of filtering, again, with the cohorts. We can do that. A little further down, we can actually look at some of the details, right? So correct predictions and incorrect predictions. So we can start looking at, what data is actually producing like bad results, right? That the model is not predicting properly. Feature importances. So aggregate feature importance, right? We talked about that. As well as the individuals. So we can see that in this case, pregnancies happens to be the most impactful one, followed by age. So both of these, we can look at some statistics and play around with those a little bit in the start. A lot of these are all very interactive as well. And if we come up a little bit, we can look at the individual feature importance. And for this one, because we're talking about an individual one, we need to select one of the rows, right? So I'll take an incorrect prediction here, the very first one. And we can come down and look to see the importance of that. So it's still pregnancies, but you see some of these have shifted a little bit. They're not as important when it came to making the decision on that one row. So So that's not too bad. Okay, now that everything's connected up at the top, right? So we have that compute instance connected. Now we can get a little more out of this. And so if we go over the heat map, you notice that we can use that compute to do some of this filtering, really. So let's take, how about, let's take BMI, right? And when we select one, we can see the different groupings of BMI and what the error rate is on those for that. So you see there's one group that is hitting 50%. So we might want to drill into why there's an error rate that's so high in that section. But we can cross-reference this with another feature. So for this one, it's just a little hard to get to. There's age, it's a little further down. And what we get is the heat map as a matrix. So the age going horizontally, the BMI vertically, and you see down here you get like 62%, and we can look to see what BMI that is, like what range, as well as what age range that is. That we're getting a high level of error rates, right? So you can work with that to go through it. So there really is a lot that you can sit and play with the responsible AI. Let me show you cohorts. That's probably the other big thing that just to get you started with this. Now cohorts, again, this is a way of filtering. So let's do one. How about like say age, if I can spell it right. There we go. Age greater than 50. All right, let's do that. And what we're going to do is base this filter, because it's a subset of data, based on the data set. We'll say I want to select age, and we'll say greater than or equal to. Actually, it should be greater than, but whatever. That's close enough. 50. All right, you get the idea. As soon as we do that, and there's a save, but there's also a save and switch. When we save and switch, we'll actually apply this cohort, it really kind of behaves like a filter, to all of the analytics that are on this page now. So things like the heat map changes, we can see things like the age greater than 50 compared to the all data. So this can help us, isolate cohorts and start comparing it against the rest of the data or even other cohorts for this. Okay, so it won't go through everything. There's a lot into it. So responsible AI, it's really important that you really focus on it because after all, we really want to have good, fair models. Okay, so with that, let's come back over to some content and we'll wrap up this video. And that brings us to the end of this video. I hope you enjoyed our discussion on registering models with ML Flow and the Azure Machine Learning Workspace and how to work with the responsible AI dashboard. I hope you'll join us for the last video of the course where we'll be covering how to deploy our models. Thanks for watching. Hi there. My name is Neil McIsaac, and I'm a Microsoft Technical Trainer. In this video, we'll be covering how to deploy and consume models using the Azure Machine Learning Service. More specifically, we're going to be looking at how to deploy a model to a managed online endpoint, followed by how to deploy a model to a batch endpoint. So let's get started with deploying to a managed online endpoint. If you recall from one of our previous videos, an endpoint is used to expose an API for the model that can be reached over the HTTPS protocol. That way an application can send an HTTP-based request with all of the input data and receive a response with the prediction back from the model. Online endpoints are used for real-time scenarios. In other words, we have an application that needs an immediate prediction. So for example, perhaps we have a website that needs to predict what is the best choice for advertising based on the browsing pattern of the customer. In order to service the request, we'll need some compute to host the endpoint. Earlier in this course, when we were talking about compute, you might remember that we have a couple of options that can be used to host our endpoint. We can host our endpoint as either a managed online endpoint or could host it within a Kubernetes cluster. Managed online endpoints are much easier to deploy since the Azure Machine Learning Service will manage all of the underlying infrastructure that will host our endpoint. So for this reason, we'll be focusing on that. If you're in a situation where you need more control over the hosting environment or need the ability to scale to much higher levels, then Kubernetes would probably be a better choice. We really have two different scenarios to deploy a model to a managed online endpoint. The first one is used with ML flow models that have been registered using an ML model file with the Azure Machine Learning Workspace. This is definitely one of the benefits of registering your model with a model file, because deploying is just a matter of specifying a few settings when we create the deployment for it. The other scenario is if we have a custom model. The thing with this one is that we need to do a lot more work. Specifically, we need to still register the model, but we'll need to do this a bit more manually by specifying all the necessary files, followed by creating a scoring script, which is needed to define how the request to the endpoint will communicate to the model and how the predictions will be sent back. We also need to define the execution environment, and then we can create the deployment and deploy our model. One of the benefits of using the Azure Machine Learning Workspace to host our endpoints is that we have the ability to manage our endpoints. So we can do things like list all of the endpoints. We can see the details of the deployment logs of the endpoints. We can test our endpoints. We can manage the different versions of our the deployments that are deployed to the same endpoint. When you see on the slide here, we see a graphic with an example test against a specific deployment version for an endpoint. In this case, we can pass all of the necessary input data to our endpoint and see if we get the correct response back. You'll notice that the deployment version of the endpoint is set to blue. We can name our deployment versions whatever we like, but the blue name that is being used on the slide here is a great reference to the deployment's ability to do things like blue-green deployments with different versions. You know that they say a picture is worth 1,000 words, which makes me curious how many words a demo might be worth. So let's jump over to the portal and check out a demo on how to do an online deployment. All right, so looking at how to create an online endpoint here. So I have a notebook that's open, and we're going to use this to go and define and create our endpoint. And the first thing that we're really doing is defining the endpoint itself. We'll do deployments to this in a little bit, but so we use the managed online endpoint class, and we're going to give it a name, a description. We're going to, in this case, we have the authorization mode to set to be key-based. And we're going to set the name to be something dynamic. So we have a date time that's being added to the endpoint name. And we're going to run that to define the endpoint. We need to go deploy it here in a second. But so this is all done. It's pretty quick to do that. So let's come down a little bit, and we are going to create or update the endpoint and see what that result is. Now, the endpoint itself, you can sort of think as like a big label to say, hey, here's an endpoint. We're going to put deployments to it. So even though it says, by the way, this is a notebook that is out online, so we have these warnings in here to wait until the endpoint is created. But this actually doesn't take too long because there's not much there. So let's go talk about the deployment itself. The deployment is what does the work, right? So in order to do the deployment, we do need an ML flow model. So we see that we're defining our model here. We have like the model object, the deployment that we're going to use, managed online deployment. So different than the endpoint, right? Deployments go to an endpoint. So we define our model here. We give it a name. So in this case, blue. We're going to go with the blue-green sort of model. And we specify what endpoint we're going to deploy it to. Now, because the deployment does the work, we also need to define the compute for it. So we have the type of compute, we have the instance count, in this case just one, so we're going to keep it pretty low key. But you can scale this to be a lot more. Package all this up as a managed online deployment, right? So I think that looks pretty good for that. Let's go back here, see if our endpoint is done. So these usually don't take too long, but there we go, it's just finished, I think. It's a little slower in the notebook. Saw the notification, but the notebook's going a little bit slower. Should pop up here any second. There we go. So you can see that this is done. The provisioning state is succeeded. You can see that way over here. And so now we can come down. Once that's there, we can send a deployment to it, right? So for me, I think of those endpoints as a way of grouping deployments, right? These are all the deployments that kind of belong in the same category. So this is going to be the blue one. That was the definition. We need to deploy this as well, like, and I mean, to go create the deployment to make it go. So when we run this, the begin create or update, this will take a little more time, right? So we see the creation here in progress, and this will take a little bit to go. So let's see a few other things here. One of the things we can do this later, is we can change the amount of traffic that goes to a deployment. Now, this is a kind of simple example here, but real world, I may have more than one deployment to the same endpoint. So think, blue, green. I could say that blue gets 50% and green gets 50%, and I can play with the traffic. Now, in this case, we only have one, but we're going to set it up so that 100% of the traffic is going to go to this deployment, right? It's the blue deployment on this endpoint, right? So we're just specifying which deployment to really use. So that one, that looks pretty good. Now we do need this to kind of finish before we really do that. So something else, just while that's going, we'll talk about testing it, right? So testing it, we're going to go, once that's deployed, we'll invoke the endpoint. And in order to do that, we're going to send a sample JSON file. So let's go look at that. The sample JSON file is just really all the columns that we need to send into the model with its data. So for example, pregnancies here is, this data is 0 pregnancies for this one sort of row of sample data. And what we expect when we invoke it is to send that data to the endpoint and get that prediction back. So, based on the data, should the result be that they're diabetic or not? And we can see diabetic. If it returns a 1, they're diabetic, and if else, they're not diabetic. Okay. So again, it still takes some time for the deployment to go. So at this point, we're just really going to watch this for a little bit and wait for it to finish deploying, and then we'll see those other things test out. For those of you that are watching the recorded version of this course, we've sped up some of the video to save you some time. The typical wait for this can be much longer in real life. All right, finally, we have our notification that the deployment has completed, right? We see that everything's come back. The provisioning state is succeeded as well. So that looks good. So let's come down and just go back to the code that we were talking about earlier. So as far as the traffic goes, we can say, hey, let's make sure that 100% of the traffic is there. And again, this makes more sense when we have multiple deployments, but I think you get the idea that we can play with what percent of the incoming traffic goes to which deployment. So not all of the incoming traffic necessarily goes to just one deployment. We can play with that. This will take, this one doesn't take too long to really update that. Let's give that a minute. There we go. So that update's completed. We see the notification for it. So let's come down and do a test. All right, there we go. Just waiting for that to return. So, all right, provisioning state succeeded. So let's come down and test this deployment with some code. So I showed that sample data JSON file earlier. So let's just run this. We're going to send that data back and forth. And what do we get? The result is that the prediction is that this person would be diabetic. All right, so that gives you an idea of how to use these real-time endpoints. Let's jump back to the content, and we'll talk about batch endpoints and what those look like. The other major option for deploying our model is to deploy it as a batch endpoint. So let's take a look at that next. Batch endpoints are different than online endpoints in that they're designed to process a batch of input data all at once. The endpoint is still an HTTPS-based endpoint, but where online endpoints are sent input data and receive a prediction back, A request to a batch endpoint is used to trigger the batch scoring job. In other words, we'll use this type of endpoint to basically say, go score that pile of data over there right now. A really useful scenario for this is that we could use it to trigger scoring from other services like Azure Synapse Analytics or Azure Databricks, since those services are really good at data engineering, which is all about data movement. So doing that ETL or ELT process, which is a big part of preparing data for model training, is very similar to what we might do to prepare data that needs to be scored by the model. Essentially, Azure Synapse Analytics or Azure Databricks can do all of that preliminary work to prepare the data that needs to be scored, and then call our batch deployment to tell the Azure Machine Learning Service to go score that data. Another difference between the online endpoint versus the batch endpoint is that when a batch endpoint is triggered, it actually creates a job that's submitted to the workspace to be executed. And you can see and monitor the job within the workspace. The first thing that we need to do is create the batch endpoint. We can create a batch endpoint using the Studio interface, using the GUI, or we can use code such as the Python SDK, like you see on the slide here. So in this code example, we're simply using the batch endpoint class, where we assign a name and a description to the batch endpoint, and then submit it using the begin, create, or update method for deploying batch endpoints. Next, we need to configure some compute for the batch endpoint to run. Because it's a batch endpoint, we need to configure a compute cluster to do the scoring of the data. We can configure this either in the Azure Machine Learning Studio, or we can do this with code. So in the example here, we see that we're just creating a compute cluster using the Python SDK, which is something that we looked at earlier in this course. Keep in mind that this compute will spin up, process all of the data, and then shut back down based on the idle timeout, which in this example is set to 120 seconds. Depending on your scenario, if you have a lot of data to process, you might want to configure both the size and the max instances to be higher values so that we can maximize the amount of parallelism when we're processing all that data. That might seem like it would be more expensive, but in a very general sense, if we use twice as much compute, but it takes half the time to actually accomplish the task, the cost is sort of roughly equal, very roughly. The reason why this can work is because we're only paying for the compute when it's running. The next thing that we need to do is to deploy the model to the batch endpoint. Similar to online endpoints, a batch endpoint supports multiple deployments that we can use for scenarios like versioning or blue-green deployments. That being said, we do need to specify one of the deployments to be the default deployment. The reason for this is because when the batch endpoint is called, the caller can specify which deployment should be used to score the data. So, for example, if we deploy two versions to our endpoint, so version 1 and version 2, the caller could choose to score the model using version 1 or version 2 when they make the request to the API. We need to have a default deployment set because the caller can leave off which deployment to execute when they submit the request. They don't have to specify version 1 or version 2. So if that happens, the batch endpoint will use the default deployment to do the scoring. If we're deploying an ML flow model to a batch endpoint, things get pretty easy. We simply have to configure the behavior on how the model will execute when it's called. So we need to specify things like instance count, which is the number of compute nodes that we want to generate for the predictions. The max concurrency per instance, which is the number of parallel scoring scripts that should be run on each computer node. The mini batch size, which is the number of files passed per scoring script when it's running. The output action, which specifies what we do with the predictions. So do we just have one single file summary of everything, or do we append the prediction to each row of input data? And lastly, we need to specify the output file name where we'll store the results. If we're deploying a custom model to a batch endpoint, then similar to online endpoints, we need to specify a scoring script, which is really about the details on how the data needs to be passed into the model to do the scoring. We also need to create an environment for this, which, if you recall from earlier in this course, defines the execution environment where the scoring script will execute. This way we can load any dependencies or required libraries that might be needed by the scoring script. The last thing we need to do is to create the deployment itself. If we're doing this using the Python SDK, we could use the batch deployment class to configure that deployment for us. Now, assuming that we've successfully deployed everything, we need to use our batch endpoint to do some scoring. This is a little bit different than what we would see for an online endpoint because we need to tell the batch endpoint where our data is for input. In the Python SDK example here, you can see an input variable being defined as a reference to a data asset that is of type URI folder. After that, we can invoke the batch endpoint by calling the invoke method. And of course, we need to pass the endpoint name and our data reference to the method. In this case, the input variable that was previously defined. Once the batch endpoint is invoked, we can see the job that spawns in the Azure Machine Learning Studio and see if it ran successfully or not. The predictions that it generates will be stored in the default data store. All right, so let's try and put all that together with a demo. All right, so let's look at going and working with a batch endpoint. So again, we're going to do this in a notebook. So the first thing we want to do is register the model, right? Similar to what we did with the online endpoint. So an ML flow model, nothing really different there. So let's get that registered. So that doesn't take too long. It's pretty quick. Then we're going to create a batch endpoint. Again, batch endpoints are similar to the online endpoints, and I mean that like in the endpoint context, where we're going to give it a name, right? So we have a name for this, and so we're just modifying a little bit so we have a unique name for it. And then we're going to define the endpoint itself. And the endpoint is really like that label, if you will, to where deployments go. So this part, we're going to create the batch endpoint using the class. There's the name, description, and we're just going to create. There's nothing really that different than what we did earlier with the online endpoint. So think this package. So the creation's going. It's completed. It's that quick for it. Really just a quick definition. Now, here's where the magic happens. Create the deployment, similar with the online deployments. This is where we're defining where all the work's being done. But in this case, it is a batch deployment. So we're going to specify a little bit more than the other one. We're going to use the batch deployment constructor here. And we're going to give it a name, description, the endpoint name of where we're going to send this deployment to, right, where it's going to be wrapped in. The model, compute, the instance count, all of the settings around the compute. We're also going to give it the output action. Remember that we're going to batch everything, so we want to know where the results go to. In this case, predictions.csv. And how it's going to handle that, we're going to append to this file, right? So we're going to append rows to that file. And a few other settings like retrying and all that, but basically it's different because it's just settings that kind of represent doing a batch. So let's get this submitted. And similar to our online endpoint, this can take a little bit of time to really go. However, not as much time, because in this case, we're not really getting it to go. We don't need the compute to go running or anything like that. So we can move on. So let's talk about the default deployment that I'm highlighting here. It's important that with batch endpoints that we actually specify a default deployment and set that, because when a caller comes over to call this, they don't have to specify which deployment they're using. So I'm running that. What did I forget? I think I might have been just a little fast on this. All right, so let me run that again. And yeah, so just, that should have ran okay. That's all done. All right, so I think I was just a little fast on this, and that's probably fine. So let's run that again. There we go. So that submitted okay. So again, you know, we can have multiple deployments in there, and making sure the default is there is just if somebody calls it without doing it, it's fine. All right, let's set up the data for this. So when we use it, we want to have a bunch of data for it. So let's look at what I have here to test it. So a bunch of patient data. So think there's, I think there's 100 rows in each one of these, something like that. They're not terribly big, but we're going to set it up as a data asset, right? So this is going to be a URI folder, and we're going to go and create that asset so we can use it. So this is the data that we're going to send to the batch to go and score. So this goes pretty fast, right? We're just setting up that data set. And at this point, we just want to retrieve it to make sure that we're getting the data set, the unlabeled data set, back from the machine learning service. And then we're going to submit the job, right? So when we call a batch deployment, we need to send the data. So our input is going to be that data, and we're going to send that to the endpoint. Remember that when we trigger batch endpoint, we're really saying, hey, go spawn a job and do all this. So when we create the endpoint, when we invoke it rather, we need to pass that input data that we just specified, right? And then we're going to just retrieve that job back. So let's give this a go. Oh, what'd I miss? Oh, you know what? Yeah, sir. Okay, so it's not, for some reason I was thinking something was still deploying, but let me go back and just look at this real quick. I think I just forgot something very silly. And, oh, you know what? This is what happens when I try and talk through this a little too fast. So setting the input, we forgot to run that. So now that we have the input, let's go and create that endpoint. Let's invoke that endpoint with the input. Now, this is going to take a while because it needs to spawn the job. The job needs to go and create the compute and everything, have that getting really started. And then it has to do all the predictions to actually process the data in batch. And this isn't really set with a lot of compute in this example, so it'll take a little bit longer. And then we'll get the results after that. Okay, so let's leave that go, and we'll keep an eye on it here and there, and we'll see how that works. Since this video has been pre-recorded, we've sped up this section to save you a bit of time waiting for this to complete. All right, so we're still waiting for this. I'm just going to make a small little change here. Let's just edit this cell. So I'm going to get rid of making that endpoint. So we just retrieved the status of the job, right? So it's that wasn't updated. So it's running. Just want to see if it was complete or not. So let's give it a tiny bit more time. And once it's running, usually it doesn't take too long to go, but it will take a little more time to finish. This part of the process can take some time, so let me hit my magic fast forward button to jump to the good stuff. All right, there we go. We just got the notification in, so it looks like the batch is completed. So let's just double check here. And yeah, sure enough, it is marked as completed. That's great. So let's go look at the results for this. So what we're going to do is we're going to download the output name score. So where the scoring is we're going to download that to a local path for this script, right? So we're going to do that, and that will let us to go and read the predictions like CSV and stuff like that. So we got that. Let's go see if we can read that. So that data is all read. All the stuff in the file is read in the data variable. So we're going to just do a little cleanup here for new lines. But one of the things about this is it's going to kind of show up a little bit messy for that. There's a kind of an error in it, but don't worry about that. The point is that we're actually reading the data, and we can see the results from it. Now, it's a little hard to interpret here. So what we'll do is I'll show you where this is in with the job as well, right? So let's yeah, I think we're good here. So let's jump over and see the data in another spot. Right? So yeah, that's just an error come back. I wasn't sure if it's just there a little bit fast, but it that CSV file, predictions, is actually, because we downloaded it, it's actually just sitting here. Let me just refresh this. Sitting here in our local folder, right? So when we download it, so the predictions, a little easier to see. What this basically is the file on the right-hand side has a bunch of rows, and we see the predictions in the middle here. All right, so see a lot of people getting predicted to have diabetes. The way over on the left-hand side is the row identifier, so we see the different rows from the file. So patient data 1, right, is marked to be diabetic, and so we do see the results of what's going on. So it's basically which row in that file is coming back for that. So with that, we do see the predictions coming back. That's what we're looking for. It's a lot of data that was all processed at once. That's what a batch endpoint is really designed for. So, all right, with that, let's jump back to the content where we're going to wrap up this video and wrap up the entire course. Just to wrap up our section on working with batch endpoints, if anything goes wrong, we'll need to troubleshoot it. As we've seen, a batch endpoint runs as a job, so troubleshooting is really just a matter of just looking at the job execution. However, the actual scoring process will show up as a child job. And under the Outputs and Logs tab, you can find some job status files under the Logs user directory. Specifically, you can see a job error text file that will summarize any of the errors in the script. You can see a job progress overview file that will give you high-level information about the number of mini batches that were processed, for example. And you can see a job results text file that will show you any errors with calling the init or run function specifically that would be in your scoring script. And with that, that brings us to the end of this video on deploying models and to the end of our course. I sincerely hope that this video series has helped you with your learning journey with a better understanding of the Azure Machine Learning Service. Since we're at the end of the course, I'd like to take a moment to remind everybody about the importance of certification. Certification is a great way for you to confirm how well you know how to use the Azure Machine Learning Service. And to reiterate a point that I made at the beginning of this video series, is that you can really think about certification as the goal to your learning journey. So you can think of all the topics on the DP-100 certification exam as being all the things that somebody that's working in this space should know about the Azure Machine Learning Service. That means if you really want to be a professional working in a space, you really should be at the level where you could pass the exam easily. And one way that I like to phrase this is that you will find out one of two things if you do the exam. Either you pass the exam and walk away with the confidence that you know your stuff, or the exam doesn't go as well as you'd hope. You can think of it as somebody simply pointing out some additional things that you should know. And in that sense, I would much rather that you make your mistakes on the exam where you can walk away, learn it, and then come back and try again, rather than making those mistakes on a real-life project, which can have some really serious consequences. And with that final thought, I wish you all the success in your future, and I hope we see each other again. Thank you for watching.